Good morning, everyone.
Good morning, madam.
Good morning, Ashutosh. Good morning, Mr. Ganesh. Good morning, madam.
Morning.
Good morning, Dr. Poonam Arora. Nice to see you after a long time.
Yeah, same here, sir.
Good morning to all. As
Morning,
we are
sir.
all aware, that in India, we are still using the GPS time. We do not have our own Indian Standard Time to be disseminated in all networks, banking sectors, etc. And that's why we are also facing a lot of problems for not having our own time. This is the starting done by the National Physical Laboratory. They have their own ISP, taking their this time ISP is synchronized with the BIPM, and then we are having the Indian Standard Time at National Physical Laboratory level, but it is not disseminated thoroughly, as ISRO has already started Navik system today to understand what is the GPS, how this Navik system is working, how we are transmitting, how we are disseminating this time in India, and what is the next plan of the government to has this time disseminated in India so that all the networks, telecom operators, internet service providers, banking sectors, etc., have their Indian Standard Time. This is just an initiation, as we have with us the scientists of ISRO, Dr. Ganeshan sir, Dr. Poonam Arora madam from National Physical Laboratory. And first of all, I would like to welcome my additional secretary, ma'am, Mrs. Dy.Dir, who is always burning light behind all these initiatives we are taking for the dissemination of not only time, but to safeguard the interest of consumers in the country. As we are having this last more than 2-3 years, we are closely working with ma'am, and she is always a vital force to work behind all these new initiatives in the country. We have requested her to kindly come and bless us, inaugurate our conference workshop, today's workshop, to understand, to just create an awareness among the people of the country. What is time? How we are planning and what is our next plan, how it will affect the whole industry and the whole country when we will be having our own Indian Standard Time. We have requested ma'am to kindly come and inaugurate our conference. She is so kind enough, having so much lot. I know that how much she is busy. This last 8 p.m. many times I have seen that she is coming out from our office at 8 p.m. even after 8 p.m. morning. Last week I remember whole of the day, Saturday also she was in the office. Ma'am, but certainly due to few people, somebody was telling me that in India we are basically 20% of the people who are working, and everybody sees these 80% who does not work. So the people think that we are not working, but these 20% people who are actually working 80% of the work are the guided force for all these developments which are happening in the country. And now certainly we are working towards becoming self-reliant, self-atmanirbhar. And first of all, I would like to request you to kindly bless us for this for this workshop, and kindly help us, kindly bless us for making this legal methodology, to take this legal methodology up to the next height. Ma'am, please. Nidhi, ma'am, as we are all aware, she is the CCPA, and CCPA is doing a wonderful job.
Namaskar.
Sorry, ma'am, I just wanted to share one bit.
Yes, please. Go ahead.
Ma'am, one more information, which is very important information about the CCPA for these helmets, pressure cookers, and now misleading advertisements and a lot of other things which CCPA is doing in the interest of consumers. I have never seen since last for more than 20 years I'm in the department. I have never seen that actually we are working for the large society of the consumers. One small work working for the whole society. Thank you very much, ma'am. Certainly, we are looking towards you for doing better for the consumers. Thank you, ma'am. Please.
Namaskar and good morning, everyone. I feel very privileged and honored to be invited in this workshop, which has been virtually a weekly workshop with the stakeholders, wherein we try to see the new issues that are being taken in the ever evolving world to the consumers and to the stakeholders with a view to make everybody's understanding better. Now, we are a country which has measured time since time immemorial. For example, in the Panchang, nobody say, for example, we do not have those issues where we look forward to a religious leader to tell us when to celebrate a festival. In the villages, everybody knows, for example, when the Kumbh Mela is going to happen. Why? Because we have basically, we have as a community and as a country, have an understanding of time. Now, in the modern times, it is equally important that the accuracy of time and the dissemination of time is uniform across the length and breadth of the country. As Ashutosh ji has already mentioned, time is something which is not only of strategic importance, but it is also important in the sector of, say, financial management, in commercial area, in banking, insurance, and there are other so many sectors which are very, very dependent on the correct time. But what is it which we are doing differently? This is what we must ask ourselves, and this is what is the understanding that has to be developed. What we have been dependent so far is on the GPS system. While we are taking and trying to see that the BIPM time, which is our reference clock, is the time on which the clocks of the entire country are basically based on. But when we actually made NPL as the timekeeper of the country, we still could not disseminate it in the way we would have wanted. Also, how to accurately ensure that the time is not only disseminated, but it is also received at all the, all the cities everywhere. Because we are not like USA, we do not have time zones. So probably it's going to be very interesting to develop this understanding as to how we are going to make a difference with the completion of time dissemination project with our ministry. And what are going to be the next challenges, the challenge for the next, say, phase, wherein we can take the nation forward. With these, I think, as an opening remark, I would now urge the experts, the people who are, the masters in this, to convey their message and to ensure that all the stakeholders who are basically who have joined this webinar also get to understand, better their understanding about this whole project. with these words. I also feel that this is in a very as a very small step. This is one way in which we are trying to reach out to our stakeholders. We are trying to reach out to different segments in the society. And since the time dissemination project is going to, I'm sure, be completed by March 2023, we would have by that time tried to, evolve a common strategy about this whole project. Over to you, Ashutosh. Thank you very much.
Thank you very much, ma'am. You are always I tell you now that this is you are the light behind us for this legal metrology in the country, and certainly, ma'am, we are always looking towards you to guide us, to help us, to bless us for the better citizens of the for the better to become the better citizens of the country, and we can serve the nation in a better way. This is the only purpose, ma'am. Today, with your blessings, we have Dr. Poonam Arora from National Physical Laboratory and Dr. Ganeshan, who is from ISRO, and these are the experts of the time and all these things. I'm blessed to have these people with me, and with a short notice, they accepted my request and ready to enlighten our people, our the country people, are the stakeholders, so that this information can go. And when we will start disseminating, and when we will make some provisions, some guidelines, some rules, when we will bring, all the people must be aware of that. That certainly India is looking towards the next generation, next century. So, ma'am, thank you very much, and certainly I would like to request you to kindly continue your blessings like this only. We will always request you to come. When you come, I think that we feel ourselves that we are powerful. Thank you, ma'am. Thank you very much, ma'am. Ma'am, we have with us Director Sir Dikshit sir. Dikshit sir is also there. Sir, are you listening us?
Yes,
Sir,
yes.
please kindly say, sir, a few words so that we can start this opening session.
Respected Additional Secretary Mahodaya, uh, Senior Scientist in Time Dissemination from NPL and other organizations, Mr. Ashutosh Agarwal. So, the day we are coming nearby to disseminate the time disseminations, the challenges coming before us are very high, and we are thinking more than required, because it is natural that being the implementing authorities, we have to consider the all the sectors, that no sectors may be unleft when we are implementing the time disseminations, and we have to ensure that all the sectors who are interested to take the benefit of time disseminations, they may get it. This is not the matter of only security, banking, insurance, and cybercrime, or like this only. This is the issue of the medical science also. This is the issue of the scientist also. This is the issue of even school, college, universities also, because the thinking will be changed and idea will be changed. What research paper now these days be written, those line will be also changed. So you have to think that how tremendous changes are likely to come in the country when the time dissemination will be started, and we might be not understanding that there may be the crores of the organizations lakh and lakhs of the organizations, they will approach us, and we have very limited manpowers and infrastructures. We may not hear, and our complaint may be more than what we think. So that's way that this uh, time dissemination is coming before us. So it is not a new technology, but it is a great challenge also. One time I was hearing from some senior scientist retired from NPL that he told that once the atomic clock is set, then it is set and it will continue to run. And one day uh, we discussed that how to ensure that all the atomic clocks are being connected with the BIPMs. What is the methodology that this is really connected with the BIPMs? Are we getting link? Our synchronizations are not there. These are being challenges. So one thing was in my mind, I could not explain that very day, that the geostationary satellites are there, and all these geostationary satellites are having the atomic clock also inside. And that way, uh, the time is connected from one country to another country through the atomic clocks, connecting the geosatellites. So I think our respected scientists might be knowing more than me. I have learned from them only, because our project is depending upon National Physical Laboratory and their scientists and dear friends like Aswal Saab and Ashish ji, uh, Madam Arora, and so many other peoples who are here to address. They will address that how to ensure that the time will be correct, at least at the all the RRSLs, and how the people will get it correctly and within the boundary as per their requirement, because challenges are coming before us. It is huge and huge, and we have the limited number of peoples. Even we includes total NPL scientists also to work on this very project. I think that there will be the shortage of scientists and manpowers for the time dissemination. With this the very words, I give thanks to Ashutosh ji for kind motivational words, to Madam Nidhi Khare, Additional Secretary Sahiba, and I am waiting to hear the words of the scientists and other technocrats who are taking interest in this very field. Thank you, Ashutosh.
Thank you very much, sir. Thank you for your kind words. And certainly, sir, we will do our best for this, for the society, how we can develop this society, how we can have good standards in the country. This is the only purpose for us. So, you have done a lot of work in legal metrology since last more than 10 years. You are working and day and nightly for developing the standards, for developing the legal metrology system in the country. The country will always be thankful to you. Even you are, as I know that you are a very well-known figure in the OML also, International Organization of Legal Metrology. That means, sir, we are trying to learn from you people who have actually spent, not I should say spent, actually who has put the whole life for the development of the standards and the good life for the citizens. Thank you very much, sir. Thank you. So now we have with us Dr. Ganeshan. As we are all aware, Ganeshan ji is a well-known scientist in the field of this time dissemination, and he's a basically scientist in ISRO. And I think most of us are aware of his name, Dr. Ganeshan sir. Mr. Ganeshan is basically right now he's the Deputy General Manager in INFO CTF in STRAC. STRAC is basically responsible for this development and dissemination of time through their NAVIC system. He is engineering graduate from Thantai Career Government Engineering College of Technology from Madras University. He has obtained master's degree in satellite technology from the Department of Aerospace Engineering, Indian Institute of Science, Bangalore. He's working with the ISRO since 1997 in telemetry, tracking and command network, STRAC, and has worked in the field of mission operations and health analysis of Indian remote sensing satellites, and has been closely associated with IRS-1C technology experiment satellite and the Resource Set 1 satellite. But I would like to request Mr. Ganeshan to kindly enlighten us about the new standards, how they are using the satellite system. As we know that in India, we are having seven NAVIC satellites, geostationary satellites, which are working for this region of Indian region, Asian region. And he must be aware of all. More than that, Mr. Ganesh, can you start, please?
Yeah, good morning, sir. Am I audible?
Yeah, you are audible, please.
Give me a minute for me to share my PPT and then we can get started.
Please.
So is my PPT visible?
Yes, sir. It is just coming. Yeah, it is okay.
Okay. Good morning, Dr. Nidhi Khare, Dr. Ashutosh Agarwal, my co-panelists, Dr. Poonam Arora, and all the attendees. It's a pleasure and an honor to be here. And thanks for the nice introductions also. Yes, I've been involved with the NAVIC project right from its inception. And when we started this project, I would like to give a small background. So in 1999, when we had this Kargil war, we were actually subjected to a service denial by GPS. The Americans wanted to have a neutrality over the region, and our soldiers who were fighting the war were actually denied of GPS signals. Then the government thought that we should have our own satellite navigation system. It could be a modest system. It need not be a very state-of-the-art, or it need not be something which is as ambitious as the GPS, but it should be under sovereign, self-reliant control. And with that in mind, a project was sanctioned and approved in 2006. And 2006, we went about designing the constellation, what kind of satellites there should be there, the ground segment and the user segment. And here we are in 2022. We are looking at the second generation of NAVIC satellites, and really honored that we have brought. This has been one of the most challenging projects, because I have worked with precision engineering before, but nothing is as precise as time metrology. And navigation is all about time, and it's been quite an interesting journey so far. So I will just take you through this journey. So is the next slide visible?
Yes, sir. Yes, sir. It is visible.
Okay. So the objectives of NAVIC were very simple. We wanted to have, first of all, an independent satellite navigation system, which is absolutely independent from the influence of either GPS or Galileo or GLONASS or anybody. And we wanted to have a system which could provide a user with an accuracy of something like better than 20 meters. That means if you were to have a NAVIC receiver on the ground, and if you were to track the NAVIC satellite signals and fix your position, you should be able to fix your position to an accuracy of 20 meters or better. That was a very modest target, but we still was quite a challenging target. And where was this service supposed to be? It was supposed to be around 1,500 kilometers around the Indian region. So that was the primary area in which we were supposed to give a guaranteed service. And then there was also an extended service where there could be still satellites and there could still be positioning available, but there is no guarantee of the position that is available. So the guarantee of the 20 meters is always within that blue rectangle that you are looking at. The next generation, though, a lot of interest has come from the government agencies, the special users, and every other user. And now we are redefining this rectangle. So the rectangle is getting bigger. In fact, it will be touching almost the whole of Asia now. And we are also planning to augment our satellites with more satellites. And we are also planning to augment our ground segment with more resources on the ground. So, and the end target and the actual performance that we have seen is we are able to give better than 5 meters position accuracy, 67% of the time in a day. That means 1 sigma positioning accuracy is better than 5 meters. We are planning to continuously improve it. It's not very simple. So we are continuously trying to build better systems, make better algorithms and things like that. So against a specified 20 meters accuracy, we are now able to achieve something like better than 5 meters. And this service area, which we originally thought should be around 5,500 kilometers around the Indian geopolitical boundary, is now expanding, occupying almost the whole of the Asian space. So that's the introduction as far as the objectives of NAVIC is concerned. So with respect to the satellites themselves, you must be aware that the GPS consists of a constellation of 30 satellites. They have about 24 operational satellites at any point of time with 6 pair satellites. And they are each of these 24 satellites are placed in 6 orbital rings. We call them as the orbital. You can visualize the Earth, and you can visualize some bangles around the Earth placed at 60 degrees apart. And each of these bangles, you have about 4 satellites. So 6 orbital planes, 4 satellites, and therefore you have 24 satellites. Each orbital plane has an extra satellite. So should any satellite fail, then you have the additional satellite coming into immediate operation as a spare. So that's how well constructed the GPS constellation is, to a point where anywhere in the Earth, any time on the day, you are always guaranteed and a visibility of at least 6 satellites. If you are lucky, you could get as much as 12 satellites. Now, that project would cost anywhere between 15,000 crores to 20,000 crores. But we wanted to do it a little more modestly. So we did a lot of simulations and came up with this formula that instead of going for orbits, what are called as MEO or medium Earth orbits, if you look at the average altitude of a GPS satellite, it's around 20,200 kilometers with an inclination of 55 degrees and an eccentricity of something like 0.02, 0.03 near circular orbits. So, but that would be very, very costly, and that would be really a challenging project. So we thought we will come up with a regional constellation which will cover India and its immediate ambience. And we thought about 7 satellites would be enough. So we did a lot of simulations, and then we came up with this constellation. There was 1 satellite to be placed at 32.5 longitude. There were 2 satellites to be placed at 55. There was a satellite to be placed at 83 degrees, and 2 satellites at 111 longitude, and 1 satellite at 129.5. With this constellation, we will be, like you can see in the image, you will be able to cover the whole of the 1,500 kilometers contour that is in and around India. Of course, now that the requirements have come, now we are looking at a bigger contour, bigger service area where NAVIC should be available. We are trying to augment this original constellation of 7 satellites with 4 additional satellites. So in the immediate future, you will have a constellation of 11 satellites, and we'll be able to cater to a bigger area. So a bigger area in Asia, we'll be able to assure always an availability of 4 or 5 NAVIC satellites with a guaranteed position accuracy of better than 5 meters. So that's the constellation that we are looking at. As far as the services in NAVIC, you must be aware that GPS has got one civilian signal, which is free, which is available to anybody. That's what you use in your mobiles, in your automobiles and things like that. And then they also have another service which is only available to their military users. They call it as the PICO. And they also have augmented with a lot of other signals like L1C, L2C, the M code, and things like that. Today, the modernized GPS is quite very state of the art, a very modern navigation system. So when we came up with the Navic system in 2007, 2008 timeframe, we had two services: the standard positioning service, which was available to the civilian user in two frequencies, L5, which is 1176.45, and yes, 2492.028 megahertz. So in these two frequencies, we had the standard positioning service, which was available to the civilian user. Any civilian user will be able to receive these two signals, L5 and S, and will be able to fix his position and navigate himself. Then there was also a restricted service, which was only for governmental and authorized users, which was encrypted and which will have slightly, not slightly, a lot of robust features. It is not only necessarily more accurate than the standard positioning service, it's also more rugged. See, for example, in a new modern warfare system, one of the things that will happen is there will be an electronic warfare. There will be a hostile imposition of RF in our area to a point where all signals will be jammed. So the restricted service is designed to ensure that even in such a hostile system, we will be able to still survive. So that is why the restricted service is quite useful and very important to our national security. So these are the two services: the standard positioning service, restricted service, and we have L5 and S. Now, in the next generation satellites, we're also going to have another signal in the L1 frequency. L1 frequency is the GPS legacy frequency, 1575.42. So the next generation Navic will have three frequencies: L5, S, and L1. So the first of the next generation satellites, we call it as the NVS-01. It is slated for launch in November later this year. So with the other important thing about that satellite is, so far, all the atomic clocks that we have been using in our satellites were all procured atomic clocks, which we have procured it from foreign agencies. And obviously, this is a matter of concern because we can always be denied technology. We could be denied our continuity of services. But the great achievement that we have done is that we have made our own, we have designed and realized our own indigenous rubidium atomic frequency standard for space applications, which is, see, making an atomic clock itself is quite challenging, and making it for space-based applications is quite a different ballgame altogether. So a team of about 30 scientists from the Space Application Center in Ahmedabad, they have successfully realized the technology that is required for having rubidium atomic frequency standards in our satellites. And like I said, from the next satellite onwards, NVS-01 onwards, we would be having our own indigenous satellites. So we will be having an additional signal in the L1, and we will also be having our own rubidium atomic frequency standards in the satellites, which is a very good thing for ensuring Atmanirbhar and self-reliance as far as our services are concerned. So I just talked briefly about the satellites. There are 7 of them placed in geostationary and geosynchronous orbits. And they have basically two services: the standard positioning service and the restricted service. Hitherto, they were on 2 frequencies, L5 and S, and now in the future, they're going to be on 3 signals, L5, L1, S, and the L1. So are there any questions, or should I continue? I would like this to be an interactive session. If there are any questions, you can stop me and ask me then and there. I'll be able to clarify your doubts.
I have one question.
Please go ahead.
We were basically the other day when Secretary Sir was also mentioning this, that earlier we were dependent on GPS.
Okay.
Now you have told us how in that orbit you have about say 24 satellites whose the transponder area will be basically in such a way that at least 12 are able to give us this service, isn't it?
Right.
Is that right?
Right. This is as far as GPS is concerned.
And these 12 satellites are all Indian?
No. This is a GPS constellation. The GPS constellation, one more thing that you have to bear in mind, it is not a NASA project. It is directly under Department of Defense. So GPS is not a civilian satellite. It is a military satellite directly controlled by the Department of Defense, US. GPS I was talking about is having actually 24 satellites placed in 6 orbital planes, 4 satellites in each orbital plane, in such a way that a user anywhere in the world is assured a guaranteed visibility of 12 up to 12 satellites at a given point of time. Now, if I have to design and operate and realize such a constellation, that would cost me anywhere between 15,000 crores to 20,000 crores. Quite a tall order for a country like us. So we thought we'll have a regional constellation with only 7 satellites, not placed in MEO or medium Earth orbits like the GPS satellites are, but in geostationary and geosynchronous orbits, such that these satellites are always visible to us. One of the characteristics of a geostationary orbit is, if I place a satellite in a geostationary orbit, it is always visible to me. So unlike a GPS satellite which rises and sets and then another satellite comes up and takes its position, we always have one satellite available to me. So by having this constellation, what we are guaranteeing is the Indian region is always guaranteed 7 satellites at any point of time. Just with 7 satellites, I am guaranteeing visibility of 7 satellites. Now, GPS is using 24 satellites to guarantee you a visibility of 6 to 12. But I am guaranteeing you 7 satellite visibility all the time, throughout the year, throughout the day, with just a constellation of 7 satellites.
Okay, okay. So this is this called Navik satellite?
That is correct. I'm talking about the Navik satellites.
Okay, okay. I got it. Thank you so much.
Right. Can I move on? Okay.
Yes, please.
Yes. So, what do the Navik satellites broadcast? So, the Navik satellites, in a very simple sense, if you look at it, they basically broadcast, this is my position and this is my time. So, like some landmarks, like some lighthouses, you imagine you are traveling in an ocean, and you are looking at how to come to the coast. So there you have a lighthouse which is beaming some kind of a visual signal for you, where you know how to navigate and go on home in and reach the coast. Very similarly, satellites are saying in the space, my position is this, and I'm very accurate, and this is my time. So he continuously broadcasts a signal which basically contains this information. My position is this, my time is this. My position is this, my time is this. So using those signals, you fix up what is the distance between you and the satellite. Like that, if you track 4 satellites, you basically come to know what is the satellite one's position, what is the distance between you and the satellite, what is satellite 2's position, and what is the distance between you and the satellite 2. What is the position of satellite 3, and what is the distance between you and satellite 3? What is satellite 4's position, and what is the distance between you and satellite 4? So if you know all these things, you can go ahead and solve for your position and time. Now, the whole thing works only if all the satellites are synchronized to one time. That's the whole idea. So what we do is we generate time on the ground using some atomic clocks and synchronizing it to Indian Standard Time. And then what we do is we synchronize all these 7 satellites. Each of these 7 satellites have a rubidium atomic frequency standard. So we synchronize all of them to the time that we are generating on the ground. So if you were to look at it in space, they will all tick at the same time. So all the 7 ticks along with the ground tick, they will be ticking like that. So the gap between them is hardly a few nanoseconds. That's the challenge that we have. So we not just make the satellites and launch them in space. We have to operate the satellites, and we have to ensure that the atomic clocks on the satellites work, and we have to synchronize those atomic clocks to the ground time. So if all the satellites clocks are all synchronized, and the satellites are now then broadcasting their positions, then we have the navigation function going. So user receiver, if you have a Navic receiver in your mobile, you'll be able to receive the signals from the satellites, decode the position of the satellite, find out the distance between the satellite and you, and then go ahead and trilaterate or find out compute your positions. These algorithms are well known, and so any receiver will have these kind of algorithms. So basically what I'm trying to say is the satellites have to be broadcasting their position and their time, and they cannot do this. So all the functioning of determining the orbits of the satellites very accurately, synchronizing them to a common time frame, maintaining the common time frame very accurately, and ensuring that it's always aligned with Indian Standard Time is the function of the ground segment that we and my team at ISTRAC, we continuously do on a day-to-day basis. We have been doing this for the last 10 years now. We have been successfully doing it. And the users who are able to receive signals from Navic satellites and use Navic receivers for fixing their position, they are able to fix their position to an accuracy of better than 5 meters, which means it is essentially that we have mastered the technology of satellite navigation. So we know how to make navigation satellites. We know how to make atomic clocks onboard the navigation satellites. We know how to make satellite navigation receivers in this country. We know how to operate this whole system. So we are in a position where we can achieve complete independence from GPS. So, but is this all? No. We need to make this very popular. We need to ensure that every mobile has a Navic receiver. We need to ensure that all the soldiers, the armed forces, the air force vehicles, the missiles. You talk about every strategic application. You talk about power grids. You talk about communication infrastructure. You talk about the road infrastructure, railways, airways. Everybody has to come under the ambit of the satellite navigation system. So these are the challenges. So making receivers for very reliable, accurate receivers for a variety of aerial, marine, land applications, stationary applications. This is the challenge that we are looking at, and we are looking at the Indian industry. If you look at the Indian industry, they again very challenging. Very few industries are having the capability to make this receiver. So we are developing this technology. We are also hand-holding the Indian industry. We have transferred a few technology to a few industries now. So we, at least today, we can say there are about 3 industries which can make these Mavic receivers. So slowly this is building up. So this is a never-ending process. It's a very challenging process, and it's something that is continuously evolving. But the message that I would like to say is that the GPS technology is no more a very something which is a black magic for us. We exactly know how to operate it. Are we as good as the GPS? That's questionable, contentious. We may not be as good as the GPS. I'm very humble and modest to admit it that we are. But I know ISRO and I know India, we will definitely achieve something which is very similar to the GPS in the years to come. We are learning this trade and we are making rapid strides. And at some point of time, we will be able to give a system which is as accurate, as reliable, as robust as the GPS system. So moving on. So these are the parameters that the satellites broadcast. They broadcast their ephemeris. Somebody was talking about Panchang. Ephemeris is nothing but Panchang. So Panchang basically means what are the planetary positions against time. So if you look at a Panchang, you basically say you want to mark a good time. So what you do, you find out where Saturn is, where this is at a given point of time. So the satellite also says, I am at this position at this time. So it basically broadcasts its ephemeris. And not only that, it also says, hey, look, my clock is synchronized to the ground clock. But if you add these small parameters, you will get a very good synchronization. So whatever is the correction parameters that need to be added to the clock, that also is broadcast by the satellite. Satellite also says, hey, look, I am healthy. All my systems are working fine and you can use me. And if he is unhealthy and he is not supposed to be used, he immediately radiates an alert flag. So the user receiver receives an alert flag. The user receiver knows that satellite 3 has a clock problem or some other problem in the microprocessor inside or the computer inside the satellite is not to be used. So that satellite will be excluded from the solution. So there are a lot of integrity and self-help features available in the satellite so that the users do not get erroneous positions. Multiple layers of protection are kept in every layer. There is the ground segment, at the space segment, in the signal, at the user receiver, to ensure that the user is not given an erroneous position. If the user is at XYZ, I can give him XYZ position plus or minus 5 meters. That's the maximum error that I can make in my position. I should not give him any other erroneous information. I should not put him in some other position and tell him he's at XYZ. This will never happen. This is how the whole system is designed with a lot of security features and safety features at every level. So there are a host of parameters which is satellite broadcast, which enable the users to find out whether the satellites are really broadcasting correct information. So all these parameters are actually generated using the ground segment network. There is a lot of infrastructure built on the ground. So satellite navigation is not just about satellites. There is a huge infrastructure on the ground which we have established, which is continuously monitoring these satellites, maintaining these satellites in good condition, generating all the positions of the satellites, uplinking it to the satellites, and satellites are actually broadcasting these positions and the time information continuously to the user. So the user with his receiver will be able to receive these signals and fix his position. So this is how in real time, in a 24/7, 365 days, it runs. This has been running for the last, let's say, 10 years. 2013 July, the first satellite was launched. And this is right now we are looking at July 2022. So last 9 years, we have been making this continuously operational, and we are confident that moving forward, we'll have a more robust, more reliable satellite navigation network, independent one for this country. So what are the objectives of the ground segment? I was talking about the ground segment, a big infrastructure that we have. First is the housekeeping. A satellite is, for example, a very complicated interdisciplinary system. It has got solar panels, it's got a battery, it's got small rockets, it's got a computer, it's got a communication system, it's got a transponder and a host of electronics to keep it alive. And so we need to have continuous monitoring of the satellites to ensure that it is working, whether it is in the right orbit, whether it is in the right orientation, whether it is generating power, whether all the systems are healthy. So this is something that the ground segment always does. We keep the satellites in good condition, ensure that the satellite's health is always available for the user to fix his position. So that is done by two facilities called Master Control Facility, MCF, which is situated at Hassan and Bhopal in India. Then we also need to estimate the orbits of the satellites. We need to know the positions of the satellites because the satellites will be broadcasting their positions. How do the satellites know? That is the responsibility of the ground segment. So we do what is called as ranging, by which we establish the distances between the ground systems and the satellites. And using a very complicated mathematics, which I'm not getting into now, we will be establishing what is called as the orbit of the satellites. So we know what is the position of the satellite and what is the velocity with which it is traveling. So these two things we estimate it very accurately, and then we uplink it to the satellites, and the satellite will be saying, at this time, I am at this position. At some other time, he says, I am at this position. And then some other time, he says, I am at this position. So this goes on in an endless loop. The satellite's position continuously changes because it is orbiting around the Earth. And therefore, at every instant of time, what is the position of the satellite has to be broadcast by the satellite. Only then the user will be able to know where he is. So if there is an error in the orbit of the satellite, there will be an error in the orbit in the user position. So one of the reasons why one of the ways in which we are trying to improve the user accuracy is continuously improving the orbit of the satellite. So these are very complicated algorithms. Something which is sitting at 36,000 kilometers, trying to know its position very accurately, it's quite a challenging thing. So we are improving our measurement techniques, our measurement analysis, our processing algorithms, such that we determine the orbit of the satellites very, very accurately, so that the satellites are going to now broadcast very accurate positions, and therefore the users will be able to fix their positions very accurately. So this is something that we are working on. And then second thing, like I told you, the satellites have to be synchronized to one time. That means if I look at all the ticks of all the 7 satellites, they all have to be aligned in a single straight line. Aligned to what? To a ground time. So we have a timing facility on the ground. We have first generation, we did not know what is a timing facility. We did not know 13, 14 years back, we did not know what is an atomic clock. We simply bought everything, procured it, imported it. We assembled, we had a turnkey solution. But over the period of the 10 years, our engineers had a very clear idea. They studied these things. And today we are very happy to say that we are in a position to integrate and develop our own atomic clocks and our own timescale systems. So we are able to generate the time using a system called as a timescale system. The first generation was a turnkey solution. The second generation is absolutely indigenous. So these timescale systems, I will anyway talk about it later in my talk. So they generate very precise time using a set of atomic clocks, and they have the capability to steer to any reference. I can steer them to UTC, I can steer them to GPS, or I can steer to Indian Standard Time. So previously, the first generation, a few years, we were steering to UTC through an indirect means. But then we signed in 2016, we signed a contract with MOU with NPL. This is also mandated by the National Security Advisor that we need to align ourselves with Indian Standard Time. So then we signed an MOU with NPL, and we also established what is called as a two-way satellite time and frequency transfer. Very accurate methods of transferring time. We are able to transfer time from NPL to our facility just to an accuracy of 1 nanosecond. That means I know where NPL is. I will just make a mistake of not more than 1 nanosecond. This two-way satellite time and frequency transfer is again something which is new. We did not have any idea what it is, and we established this using our own satellite, GSAT 8, in a Ku-band transponder. and we have characterized this, and now we are able to establish this system also, and we are able to now align our time to Indian Standard Time to an accuracy of a nanosecond. And as a result of this MOU, NPL is actually certifying our accuracy, our stability, and our accuracy also. And every month they give us a certificate how we have performed with respect to Indian Standard Time. And we are seeing continuously that we are not more than 2 nanoseconds every month. Maximum error that we are making is about 2 nanoseconds. Now, why that 2 nanoseconds? Actually, I can get it into get my time very accurate to NPL time to accuracy of few picoseconds also. But I also have an additional responsibility that I need to be very, very stable in my frequency, because the satellites are actually going to be steered to my ground time. So I have an additional responsibility of not only maintaining time accuracy, but also frequency stability. Therefore, I steer only once in 5 days. So the error buildup that happens in 5 days is close to 2 nanoseconds. Suppose I steer every hour or every few hours or every day, I will be able to align to NPL or to Indian Standard Time by hundreds of picoseconds. I hope you are able to visualize the accuracy that we are talking about. And nanosecond is 1/10 to the power 9 of a second. That means it's 1/1,000,000th of a second, 1 nanosecond. 1 picosecond is 1,000 orders, 1,000 times 1,000th of a nanosecond. So that is the kind of accuracies that we are talking about. And that is why I said there is no metrology which is as accurate and as precise as time metrology. Today, internationally, they are saying they are able to measure 1 zeptosecond, 1 e raised to the power 23 of a second very accurately, to a point where everything else is now a consequence of time. Today, length is not measured as length, but it is a consequence of time, in the sense 1 meter is defined as the amount of distance light travels in this many nanoseconds or in this many picoseconds. So because we are able to measure time very accurately, everything else is now becoming a consequence of the measurement of time. So like I said, we are now into the picoseconds kind of accuracy that we are able to steer. But since our frequency stability is also something that we have to take care of, we steer ourselves to NPL only once in 5 days, and therefore we have a 2 nanoseconds kind of mismatch with respect to NPL at any point of time. But even that is quite astonishing, and considering that we are almost 2,000, 3,000 kilometers apart, we are able to see them as if they are our neighbors and steer ourselves very closely to them, and we then steer all our satellites to the time that I have already steered to Indian Standard Time. So in a sense, what NAVIC broadcasts is time steered to Indian Standard Time. And therefore, you can, for all practical purposes, you can say that Indian Standard Time is being disseminated by NAVIC satellites. So NAVIC is an excellent and an outstanding disseminating device for Indian Standard Time. So just as how GPS is broadcasting USNO time, if you look at the GPS equivalent, USNO, or the US Naval Observatory, is the meteorological laboratory of United States, much as NPL is the meteorological laboratory of India. They also have another meteorological laboratory called NIST, National Institute of Standards and Time, which is in Boulder. USNO is in some other place. So the GPS is working in such a way that the GPS time is steered to USNO, and USNO is one of the major laboratories, one of the most important laboratories of the world itself. If you look at Universal Time Coordinated or the International Atomic Time, 2 labs play an extremely predominant role in the generation of UTC. One is the technical physics lab of Germany, which is almost having a weightage of 0.4. The other one is the USNO, the US Naval Observatory, which is also having 0.3. You have NIM in China, which is coming up big time. A lot of measures they have got. They're really going aggressive. You have NICT in Japan, which is also a very stable laboratory. You have Verify3 in Russia, which I have visited myself, and a very, very stable laboratory. You have NPL in Delhi, which needs to really come up big time, and which is also quite a stable lab. So these are the various labs across the meteorological laboratories across the world, which are contributing to the International Atomic Time. So the International Atomic Time itself is derived as a weighted average of all these atomic laboratories. And we are now steering ourselves to Indian Standard Time. So it becomes very important that the National Physical Laboratories and the Indian Standard Time, which is generated by National Physical Laboratories, becomes very stable and becomes a major partner with respect to the UTC. And it becomes its weightage with respect to the UTC computation has to improve. So this is another endeavor that we have as a nation, as a country. And then our steering to NPL will become a little more robust and little more valuable. And then all these satellites are, like I said, are also steered to Indian Standard Time. So what you are actually going to get out of this NAVIC will be basically Indian Standard Time, which is an approximation of the UTC. So just as how GPS is broadcasting USNO time, the NAVIC satellites will be broadcasting the Indian Standard Time. And NAVIC is something which can pierce and penetrate every corner in this country. So it becomes an extremely good vehicle for the dissemination of Indian Standard Time. So these are some of the objectives of the ground segment: to generate precise time, to generate the orbits of the satellite very accurately, to ensure that the satellites are working correctly. That is also our responsibility. On all this, we are happy to say it is done in an automated manner. There is no manpower that is required to look at it. Even if I switch off all the lights of the control center, come out, this will happen automatically. This is all automated with a lot of redundancy features. So there's a lot of autonomy in the ground segment. If this system fails, the other redundant system automatically comes up and starts supporting it. Every layer, we have ensured redundancy and automation. This is one of the hallmarks of the design, and this all has been done indigenously. So this is something that we are proud of. If some of you can visit our facility, we'll be happy to host you also at some point of time. So like I said, this is the overall architecture of the ground segment. We have the satellites in space broadcasting their signals, and we have the ground segment, which is continuously monitoring it, measuring the distances, estimating the orbits of the satellites, and uplinking to the satellites. So there is a satellite control facility, and these orbits of the satellites are determined by ranging methods. I'll talk about the ranging methods as I go along. If there are any questions with respect to the ground segment, you may please ask me. I know I'm going a little fast. I know it's a little too overwhelming, this subject for you. But if there are any questions, no, please feel free to stop me. Okay, so like I said, we have a lot of redundancy in the ground segment. There are two satellite control facilities. If one satellite control facility happens to have a catastrophe, we have the other satellite control facility which will come up without any intervention and start controlling the satellites. There are two navigation centers, one at Bangalore and one at Lucknow. If there is a failure in one navigation center, the other navigation center automatically takes up. So this is the kind of infrastructure that we have built up. Every facility, that there are two time scales, two timing facilities themselves. We call them as IRNWT 1 and IRNWT 2. IRNWT stands for IRNSS network time. That is the reference time for the NAVIC satellite system. So that is generated itself by an ensemble of atomic clocks. So like you said, the communication links between all these facilities, the ranging stations, the two-way ranging stations, everything is having redundancy so that you won't have a failure or you won't have a service outage because something failed. If something fails, something else will take up. If something fails, something else takes up. So this is how the whole system has been designed, developed, and realized so that you have availability of NAVIC throughout. So this is a real-time, hard real-time system. You cannot afford the NAVIC system to be non-available. So NAVIC system has to be available 24/7, all weather, throughout the year, across the region in which we have guaranteed our service. And therefore, a lot of infrastructure has been built and designed and realized in such a way that the NAVIC system will not have any outage. That is the point I'm trying to drive. So you're looking at the ISRO Navigation Center, which has been realized in Bangalore, and this is the one which is realized at Lucknow. All these are hot redundant systems. One is a hot redundant system to the other. And what does the navigation center itself have? It has got the timing facility, which I call it as the IRWT. It has also got the data center, which is a very advanced state-of-the-art data center with all the computational facilities, the storage facilities, the archival facilities, the networking facilities with respect to all the ground stations. And it has the software. All the software is written by ISRO, developed by ISRO. The orbit determination software, the real-time software, which continuously estimates the orbit of the satellites, synchronizes all the satellites to our time. Our time scale itself is now generated with indigenous technology. So all this is housed with the ISRO Navigation Center, and we have two such navigation centers. This is the architecture and some of the pictures of the navigation center. And talking about the time scales, so the first generation time scale was a turnkey solution. The timing center itself, the time is derived not from one atomic clock, but from an ensemble of atomic clocks. So there are some atomic clocks which exhibit very good short-term stability. There are some atomic clocks which exhibit very good long-term stability. And by ensembling them, what you get is you get a time which is as good as the short-term clock in the short term and as good as the best long-term clock in the long term. So you can marry the properties of both these types of clocks and make your time stable in the short term also and stable in the long term also. What I mean by stable in the short term is something like 1 e power minus 14 is what is the stability that we are getting today in 1 second. That means the frequency deviation that I will be having with respect to let's say I'm generating a frequency. I'm generating a frequency f at instant 1. I'm generating a frequency f at frequency 2. The frequency that I'm generating in the instant 2 will not differ from the frequency that I'm generating in instant 1 by more than 1 e to the minus 14 parts. So 1 trillion, I don't know what, 1 billion, 1 trillion, so many, that many parts, that much change only I am going to guarantee in the frequency. Now we all know time is a consequence of frequency. So if I generate my frequency very stably and very accurately, my time is anyway going to be very accurate. So that is why all the effort towards frequency stability. The frequency stability in the short term is 1 e power minus 14, and the frequency stability that I'm going to get in 1 day is something like 1 e power minus 16. Now let me explain what is this 1 e power minus 16 a little bit for our day. What I'm saying is, in a day, there are about 86,400 seconds in a day. There are 24 hours. Each hour has got 60 minutes. Each minute has got 60 seconds. Therefore, in a day, there are about 86,400 seconds. Roughly, on an approximation, you can take there are about 1 lakh seconds in a day. That means 10 power 5 seconds in a day. Each second has 10 power 9 nanoseconds. Each second has got 10 power 9 nanoseconds. Therefore, in a day, there are 10 power 5 into 10 power 9. That is about 10 power 14 nanoseconds in a day. So when I say 1 e power minus 14, what I'm basically saying is 1 part in e power 14. That means if I lose or gain 1 nanosecond in a day, let's say I start my time, I compare myself with God's time, fictitious time, very accurate time. And after 1 day, I compare notes with God. And I find that I have either lost 1 second or I have gained 1 second with respect to God. Then my clock is supposed to be 1 e to the minus 14 over a day. Now, when we are saying e to the minus 16, what we are saying is we are only losing 1/100th of a nanosecond in a day. So I am maintaining time. At the end of 1 day, I would have lost just 1/100th of a nanosecond every day. And that also I am correcting, I am ensuring that I don't lose even that. So this is the kind of accuracy with which we are working as far as the atomic clock is concerned. It's extremely challenging, extremely, what you can say, complex and extremely complicated. And these are some things that, we did not understand in the first generation. And we managed to acquire all this knowledge over the period of 12, 13 years. To a point now, we are developing these time scales, and the principal scientific advisor has actually requested ISRO to be a partner in the RRSL disaster NPL redundant facilities that are being brought up. So we are actually integrating our software elements, and the system engineering of these time scales is also done by ISRO, by STRAC. And so we are happy to say that because of this technology that we have developed in-house, we are now able to contribute nationally to this very important project, where we are setting up 5 regional reference laboratories across the country, along with the disaster mitigation site for NPL. So all these RRSL labs and the redundant NPL labs are expected to be ensembles of atomic clocks, high performance atomic clocks, and steered to Indian Standard Time, very similar to what we have done in our facility. The only difference is we may not have a two-way satellite time and frequency transfer, but we are having other methods of time transfer like GNSS Common View and the NAVI Common View, which again is developed by ISRO. And it's also something which is having a similar accuracy to the GNSS, common view and all in view kind of technologies. So this is as far as ISRO's foray into timing and timing applications is concerned. So these are some of the facilities that we have realized. You're looking at some of the active hydrogen masers. The first generation masers, of course, the second generation masers are even accurate. And there is something that I would like to talk about here. So these atomic clocks, right now, the ground-based atomic clocks are still being imported from foreign countries. There are only two blocks. There is a US and there is a Russian block. And suppose something happens, which is happening right now, the geopolitical situation where we are denied, we could come into sanctions. If I go close to one block, the other block could become unfriendly to us. And we are walking a tightrope right now, trying to be non-aligned with both the blocks. But should a situation happen where some of us, where we are forced into sanctions, then the ground-based atomic clocks are a real challenge. So ISTRAC has taken up indigenization of the ground-based atomic clock also. So we have a funding from our department for developing what is called as an active hydrogen maser. We are also trying to develop a passive hydrogen maser as a spin-off of this technology. So in 3 to 4 years' time, we should have, we are also trying to work with the Indian industry so that we will be transferring this technology. So we did a survey and we found out we are spending close to 500 crores every year just buying atomic clocks in this country. NCRA is buying atomic clocks, NPL is buying atomic clocks, RRSL is going to buy atomic clocks, Department of Legal Metrology is buying atomic clocks. Every year buying atomic clocks. So we need to ensure that this foreign exchange is stopped, and we should have our own vendors, our own technology. And I think in 3 to 4 years' time, we should have an Indian active hydrogen maser, just like how we have an Indian rubidium atomic frequency standard for the satellites. We will also have an Indian active hydrogen maser and an Indian passive hydrogen maser for this country. This is something that our team and I are working, and we have achieved some progress, and we are very happy to note that some of the simulations are very encouraging, and we should definitely be in a position to have a successful realization of the atomic clock in the years to come. So having said that, some of the performance specifications, like I said, I already talked about this. Over a second, it's about e⁻⁻14, and over a day, it's about e⁻⁻16. And let's say there is a hostile situation, and I have lost contact with NPL. Something has happened. There is an electronic warfare going. I'm not able to get any contact. I don't know what NPL is or what its reference is. I have lost absolute reference to anything. Even then, if I have a capability in my time scale to do what is called as a flywheeling. So flywheeling means I don't have any reference, I'm just blindly going. But I'm guaranteeing, even if I am flywheeling, at the end of 20 days, I would not have generated an error of more than 20 nanoseconds. But actually, our performance is better than 10 nanoseconds. So let us say, and RRSLs also have these kind of facilities. Let us say RRSL is continuously steered to Indian Standard Time, and for some reason, the contact with the IST is gone in a hostile situation, and the RRSL has to become independent. Then we are designing the RRSL clocks inside RRSL timescale system in such a way that it will flywheel and be within 100 nanoseconds for up to a month. This is the kind of specifications that we have designed for the RRSL also. So these are things that we have actually mastered. The capability to flywheel and the ensembling algorithms, the steering algorithms come in handy there. So we have developed a lot of algorithms, such as the Kalman filter-based algorithm, the linear quadratic Gaussian algorithm, very complicated algorithms which were prior. These are not available in literature also. There are papers, obviously, but nobody talks about the technique by itself. So we had to do a lot of study and develop these algorithms. We are also developing some more in-house developed algorithms like the artificial neural networks based algorithms, which are guaranteeing order of magnitude and order of more stability for these algorithms. So probably in the years to come, our next generation teams will be rolling out better algorithms for the timescale systems. And so the satellites, they broadcast IRN assist the NAVIC time. They also broadcast the NAVIC minus Indian Standard Time. I told you the NAVIC is steered to Indian Standard Time to an accuracy of 2 nanoseconds. So whatever is that small residue, whatever is that small difference, that is also offset and broadcast by the satellites. So we are telling the user, so this is IRNS's time. I'm very close to Indian Standard Time. For all practical purposes, I'm Indian Standard Time. But if you still want to realize Indian Standard Time, you use this offset and correct yourself. You will actually realize Indian Standard Time. So we are broadcasting that offset also. We are also broadcasting IRWT or the NAVIC system time and UTC. Somebody wants to generate UTC for their applications, they can develop, they can realize that also. So that is also being broadcast by us. We also broadcast the IRNSS minus GPS. So if this is for interoperability, we had a discussion with all the satellite constellation operators such as GPS, Galileo, GLONASS. So we are broadcasting Galileo, for example, is entering into an MOU, has already entered into an MOU with us, whereby we are broadcasting IRNSS the NAVIC minus Galileo time. So the advantage is you can use 2 Galileo satellites, 2 NAVIC satellites, and use them as if they belong to one constellation. So in a urban situation where you are using your, let's say, a car, and there are buildings on either side, you won't have many NAVIC satellites available in your small satellite horizon that is visible to you. But there are some Galileo satellites and GPS satellites. You can use all of them as if they all belong to one constellation. So this is the advantage. We call it as interoperability. Satellite navigation constellations, they have realized, and they are all coming together for multilateral cooperation, where we are saying, let us all broadcast our time offsets and become interoperable. So this is something that IRNSS has always had in its design, and we are broadcasting it such that we are interoperable with GPS. We are also interoperable with Galileo, and these are all because of bilateral agreements which we have made with them. And like I said, the stability graphs, I don't want to overwhelm you with these kind of graphs, but basically they are extremely stable timescale systems that we have developed. This is the best that is available in the country right now. So these are indigenous, an output of indigenous technology also. Our performance with respect to NPL, that's also quite good. And this is the rough architecture that we have used for our in-house timescales. We have modified this multiple times, many iterations, much better algorithms, much smarter architecture has been prescribed for the RRSL as well as for the redundant NPL sites, where no human intervention will be required. And the systems will be so intelligent that they will know how to steer themselves with respect to Indian Standard Time. And even if you lose their the reference, they will still be able to flywheel and give you very accurate time, guaranteed accurate time. So this is the kind of architecture or the design which our team has developed at ISTRAC ISRO. Some of the timescale systems which are realized at Lucknow, we have a redundant facility there. These are some of the performances. Yeah, I talked about the two-way satellite time and frequency transfer. Again, this was available in literature. It's not something that we developed, but absolutely no idea how to do it. We are talking about sub-nanosecond kind of accuracy, first time. So we have to understand right from scratch. We established this satellite link using a GSAT satellite. We also had an allocation of 2.5 megahertz bandwidth in Ku-band. Ku-band, again, is a very challenging thing. It's prone to rain attenuation. So we had to work out our link margins and our satellite communication systems, size them correctly. The most important challenge was in the processing of the data. So once the data comes, what are the errors? There are errors like Sagnac effect, relativistic effects, free space delays, group delays in all the transmission paths. All this had to be characterized and removed from the equations to a point where NPL minus NAVIC system time is determined with an error of just 1 or less than 1 nanosecond. So that was the most critical algorithm. This algorithm was vetted by an inter-center committee, which was headed by Dr. Amitava Sen-Gupta, who is also our guru, who is the ex-director of NPL, who has mentored us in all our developments. And this algorithm was validated, and we have operationalized this. So based on our MOU with NPL, we are actually synchronizing ourselves with NPL using two-way satellite time and frequency transfer, by which we are able to accurately synchronize and steer our time to NPL time. So these are the graphs that I would like to show you. That with any other method, I had two time scales adjacent to each other, so I could measure their relative time difference using a very high performance, high accuracy phase comparator. And then I did a two-way satellite time and frequency transfer. The two-way satellite time and frequency transfer output matched very closely with that of the phase comparator. So that was the validation which we could confidently say our two-way satellite diamond frequency transfer algorithm works, and it is now operationalized also. So coming to the orbit determination part, so much about the timing part as far as the Navic ground segment is concerned. About the orbit determination part, so we have established 4 ground stations at Hassan, Bhopal, Jodhpur, and Shillong, and we are continuously operating and making measurements of the satellite's position using these antennas. So these measurements are streamed to the navigation center, where it is processed, and then the orbits are refined. So I know the X, Y, Z, and the velocity of the satellite very accurately, and therefore, and I uplink it to the satellite. The satellites will be broadcasting these positions and their time very accurately. So this is the orbit determination part of it. These are also indigenous technology, completely developed by us. And then coming to the most critical part, we also have what is called as the one-way ranging system, or we call it as the IRIMS. IRIM stands for IRNSS Range and Integrity Monitoring Stations. They broadcast, satellites are broadcasting signals in L5 and S currently. They're going to broadcast in L5, S, and L1 in the future. Now, these signals we receive at very precisely known points, and we estimate the satellite's orbit using this one-way range data. And we'll also be able to estimate how far the clock is away from our ground reference clock. So this is a very important technique. Now, the fundamental system that is available in an IRIM station is what is called as an IRIMS reference receiver. The reference receiver, you look at the third bullet, the error that he makes in the code phase is around 10 centimeter, and the error that he's supposed to make in the carrier phase measurements is around 10 mm. I repeat, 10 mm. That is the kind of error he has to make. No other error he has to make. This technology was available with only one company in the world. There is a company, Canada-based company. GPS receivers, ground receivers were manufactured by them. Gagan ground receivers were manufactured by them. Galileo ground receivers, BEDO ground receivers, EGNOS ground receivers. You take any satellite navigation system in the world, ground receivers were manufactured by them. So this is something that we wanted to break. We wanted to break this monopoly, and we wanted to have this technology. So again, if we have sanctions imposed on us, our ground segment will suffer. But this is a fundamental requirement, and our team continuously worked for about 5 years. And today we have an indigenous reference receiver. You are looking at the box to the right. The box to the left is the imported receiver, and you look at the plots. Whatever is the measurement that is done by the imported receiver is something that is absolutely measured by the indigenous receiver also. So this is also something that we are proud of. And not only this, our own in-house receiver is capable of receiving in all the 3 frequencies. So to a point where now we can confidently say, if we realize the atomic clock in 3 to 4 years, we are in a position to say that all the technologies that are required for operating the satellites and the ground segment for a satellite navigation project is available indigenously in this country. So this is something that we are working. See, the atomic clock is the only missing block in the jigsaw puzzle. Timescales realized indigenously. Navic timing receivers realized indigenously in this country. Navic time transfer receivers indigenized in this country. Two-way satellite time and frequency technology indigenized in this country. The ground segment reference receivers for the 3 bands and the antenna indigenized in this country. Atomic clock for the satellites indigenized in the country. Atomic clocks for the ground segment is something that we are working on. Maybe in 3 to 4 years, we should have that technology also ready. Laser ranging, right now we are dependent on the international laser ranging service. Again, we are setting up our own laser ranging stations in 2 places, Ponmudi and Mount Abu. Again, it's a turnkey project. We have not mastered the technology. That is something that we have to master. So laser ranging, one-way ranging, and the two-way ranging together contribute for our orbit determination process. The timing facility, the timing receivers, our two-way satellite time and frequency transfer with NPL contribute for the timing aspects of the ground segment. So we maintain time, we determine the orbits, we synchronize all the satellites to a common time frame, and make the satellites broadcast correct time and correct positions, and the users will receive these signals and fix their positions. And when they fix their positions, they are getting an accuracy of better than 5 meters. The first, when you are seeing INC1 primary, that was about 10 years back. We were getting about an error of 5.8 meters. Today, we are better than 5 meters. We are getting around 4.4 meters. So we are able to have a navigation system which is able to give an Indian user using an Indian receiver with Indian technology and position accuracy of better than 5 meters. This is the achievement as far as satellite navigation system is concerned. And this is the system that actually we are recommending it for the RRSL and the redundant NPL projects. The Navic time transfer receiver will sit in the RRSL rack. The communication between RRSL and NPL will happen not only by GPS but also by Navic. And eventually we'll phase out GPS. We'll only have Navic. We want to get rid of GPS from this country and have Navic replace GPS in all the strategic applications where we are using GPS. If you ask me, are you as good as GPS? We are not. We have no bones about saying that, but we will definitely become, and we have the wherewithal to become as good as GPS in the years to come. And with a strong NPL, a strong Navic is something that is very required for the strategic security of this country. And we are very happy to be involved in this project. And I'm extremely happy and thankful to Dr. Ashutosh Agarwal for giving me an opportunity to present some of our work and to share some of our experience in this regard. Thanks very much for your attention and time, and I will be happy to take questions.
Thank you very much, sir. This is our pleasure. You are here, and I'm looking that you are sitting in your office and working for the country, on holidays. This is very much, sir, and certainly we respect. We salute ISRO for its dedicated work for the country. I think that ISRO has. We don't have the words to say about the ISRO. ISRO has shown what they are doing for the country. Thank you very much, sir, with these words, and certainly we will request you to come again and again whenever there is a requirement of the time, because this is very much required what we are doing in the country and what is actually required in the next phase. As you have told that most of the things we are indigenously developing, we are happy and certainly we are thankful to you. Sir, I just want to ask one thing: when will be having our mobiles with Navic sensors, Navic receivers?
Right. So we already had. See, problem is India does not manufacture mobiles. That's the only problem, sir. Okay. So these mobiles are the monopoly of a few countries, few industries. There is a Snapdragon processor, which is basically the fundamental motherboard for this one. Then there are a few other companies. So we have talked with all these companies, and we have signed MOUs where now these companies which are manufacturing the motherboards for the mobiles, they have agreed for the next generation mobile sets. They will also have Navic satellites as well as Gagan receivers in there. That is one of the reasons why we are also going towards the L1 frequency. Because if you look at the GPS, Galileo, they are all operating in L1, L2 frequencies. We were operating in L5 and S. So tracking two different signals in a single antenna was quite a challenging thing. So we also got an additional signal in the L band. Thereby, we are encouraging now private operators to have Navic in their signals. So all the telephone companies, which are the fundamental OEM manufacturers, they have agreed. They have signed MOUs with ISRO and they have agreed to include Navic chipsets in their mobile motherboards. So you already have Snapdragon processors which are driving which are available in the country, and we are also looking forward for a legislation which makes Navic compulsory in a mobile. For example, I have been to Russia. Now, if you want to operate a mobile in Russia, it is mandatory for the mobile operator to have a GLONASS system in his mobile. If you go to China, it is mandatory, or they don't allow anything else in China other than the BIDU. So it's time for our government also to take a stand and say, okay, you can track GPS, you can track Galileo, GLONASS, I have no issues. But you should mandatorily have Navic in your mobiles. So if this legislation comes, then all manufacturers of mobile who want to do business in our country, who want to sell billions of mobiles in this country, will be forced to go for Navic. And at that time, Indian industry should take advantage of that fact, should be coming up with Navic chipsets. So this should be available only with our country. Right now, this is again a challenge. Having a foundry which can make Navic chipsets is again a challenge. The government is working on that. The government is aware of all these issues and they are working overtime to ensure. So we should have our own foundries where we are able to make chipsets, very small chipsets which can go into mobiles. And then if we have all these NAVIC chipsets available, then if you make it mandatory, then it will be a game changer for us. So you will have not only NAVIC available in all the mobiles that is there in the operated in the country. You will also ensure that you will have a lot of jobs created and a lot of other technologies coming inside this country. So that's where the challenge is actually. So we need to have more companies having the fundamental technology to make mobiles in this country. Only then we can have NAVIC. A foreign vendor will not have that much inclination to include NAVIC in his chipset as an Indian vendor would have. And we need more Indian vendors to come into the market.
Thank you. Thank you very much, sir. I think that you have basically opened our eyes where we were actually struggling. What is this satellite system? How GPS, how Navig, and other satellite constellations are working? Thank you very much. And certainly, I will take your help again and again for enlightening our stakeholders to understand this very important subject. And I hope very soon we will be having our own Indian Standard Time with the help of ISRO and the National Physical Laboratory. Thank you very much, sir. Thank you.
Thank you, sir. Thank you.
And sitting in the office, I'm very happy that you people are still working on Saturdays and certainly doing something better for the country. Thank you very much, sir. We salute you. Then the next speaker we have with us, Dr. Poonam Arora. She is well known in the field of time and frequency in the National Physical Laboratory. I know that she has not told me, but I read somewhere in Facebook or somewhere that she also got the award of Haryana and other states for doing excellent job, science job or technical job in the country. Madam Poonam Arora has developed this. I know that I am aware of that about this fountain, which we call in NPL. It is something which we have done in India. So I will not take more time, madam, because I understand that being holiday to keep you people busy and for this national cause. I think this is a national cause. This is not for you and me. We are not getting. You are not getting anything. I'm not able to give you anything at this for this noble cause. But certainly it will certainly help the country and our stakeholders. Our people will understand what are the requirements of time. I will not take more time. Madam Poonam Arora, please.
So thank you very much, Ashutosh ji, for inviting me for this workshop, and I really appreciate the efforts of Department of Legal Metrology and people like you to make sure that the information is disseminated to the stakeholders. And it's really, an honor for me to speak to the stakeholders also and make them aware about the work we do and the importance of time and all. So I'm also thankful to Madam Nidhi Khare, who is spending time and being here, and Dikshit Saab, as always, is present and continues to gain more knowledge by being there in all the presentations and seminars that we do.
I forgot to say one thing, ma'am. I forgot to say actually, Professor Venu Gopal Ajanta also requested to come, and in the morning when I come to know that he is some busy, but he has sent his well wishes as well as the blessings for this type of program. Thank you very much, ma'am. Please.
Yeah, I can understand. I mean, he also keeps extremely busy, and there are lots of things going on, and steering a whole laboratory is not so easy job. So I can definitely understand. But he conveyed his message to me, and basically he knows all that we do, and he's well aware of that. So I think his being aware of that I'm presenting, I think, is enough. And I'm also very happy to be a co-panelist along with Mr. Ganesh from ISRO track. So he has been the driving force behind the Navik ground segment, and they are doing really a good work, and I really appreciate their efforts. And in fact, I would like to thank you, Mr. Ganesh. You have made my job easier because I have put up the presentation, which is like slightly on not very extremely technical, but a general one to make people aware about like time dissemination technologies, and what is the importance and significance of time synchronization to one common source, which is like Indian Standard Time. So I put my presentation, and there are multiple parts, and lots of basics are also involved because I thought there are some stakeholders and many new people probably to the business. So I wanted to keep it fairly general, but many of the aspects you've already touched, and so you've made my job easier, and I thank you for that. So without taking much time, so I'll go ahead and share my screen. So just give me a minute. So I hope my screen is visible to you. Is it in the slideshow mode or not?
Yes, it is visible.
Is it in the slide?
No, it is not.
Okay, just wait a minute. I think I should have done it. Wait a minute. Okay, so now is it visible in
Yes,
the
it is
slideshow?
visible. Yeah. It is okay now.
Okay, so I picked up a topic. I mean, it's again, we are speaking about time, and so I wanted to just give a brief idea of how the timekeeping has improved over the years, like giving a bit of basics, how it all started, and how we are moving forward, like from very quickly and very rapidly in terms of improving the timekeeping accuracies, and atomic clocks, of course, are at the heart of it. So here I begin. So this is the outline of the talk. So I'm going to just give a very brief overview about NPL as NMI, what we do, and a brief journey of timekeeping, like how it has improved over the decades, especially in last 100 years. Some phenomenal work has been done in this direction, and some basics of the atomic clock, how they work, how we derive time from the atoms, and the two types of atomic clocks, because that, as the title says, from the microsecond to the optical second. So that is, I'm going to touch a little bit on the aspect of microatomic clocks and optical clocks, which are going to be the future of time standards. And then how slowly we are moving towards redefinition, possible redefinition of SI second in maybe within the next decade. And then since Mr. Ganesh has already touched on the timescale aspect, so I also want to give a brief overview of how the UTC, Coordinated Universal Time, is managed, and how the whole world is synchronized to UTC, and how time management is done on the worldwide basis. And then I come to briefly explain you about the prevalent time dissemination techniques, because I think that is something which probably Department of Legal Metrology wants to know very eagerly, like once they have their IST locally realized, how are they going to disseminate it to the common public. So I'll just touch upon that aspect, and then I'll give you, some aspect of work we do at NPL. So all the things that we are doing, and the latest mission that we have taken up when Dr. Aswal was the director. So we have taken up a mission to synchronize all the devices in the country to IST. So some brief overview over that. And then, of course, applications, like how some of the applications are critically dependent on precise time and frequency metrology that we do, and the kind of work that ISRO is doing. And to summarize it all at the end. So I think many of you are already aware of like what CSR NPL is. It's NMI of the country. So for each nation, there is one National Metrology Institute, and for India, we are the ones. And it was established in 1947. And since then, we have been keeping all the national standards for the country and keeping them traceable to the SI units maintained by the International Bureau of Weights and Measures. And this was aptly clear right from the inception. So in the Nature letter published in 1947, the task was already assigned that we have to maintain the fundamental and derived standards for the country. And this was reiterated when the laboratory was thrown open to the public. So in 1950, when the laboratory was finally, initiated by Sardar Vallabhbhai Patel. And then the task was set that we have to take care of the national standards, and this became a statutory obligation. And we were given this task also by the Gazette, by the Act of Parliament. So it's the Legal Metrology Act 2009. Of course, there were previous versions of like standards of weights and measures, and then it was remodeled into Legal Metrology Act of 2009. And under the rules 2011, it's clearly mentioned that the maintenance of national standards, all the primary standards, their upgradation is the responsibility of National Physical Laboratory. And till date, we are taking care of this responsibility. And as you are aware of this traceability pyramid in the metrology, so SI units are the apex units with no uncertainty, and then BIPM is the coordinating agency, which coordinates the standards, all standards of measurement, and then the NMIs like CSR NPL is there for India. So NMIs take care to establish the primary standards and keep them traceable to SI units. So they are really having the primary standards, and further on they take care of the dissemination, that the traceability is maintained down the line till the manufacturing and till the end users. All the primary standards and units that are maintained, they should reach the common public. So that is maintained. And why the shape of pyramid, I think people associated with legal metrology, they already know, because the uncertainty is reducing as you go down the line, down the base. So more information about NPL, I think I don't need to say much, because I think those associated with legal metrology, they also know about it. But if you have more queries to know about what NPL does, you are referred to our webpage, nplindia.org. So kindly visit the page, and you'll get to know the details of what we do and what our services are available with NPL. So with this, like since we talked about SI units, I mean, most of you must be aware. So SI system was designed, during French Revolution. It was decided that there should be one common system of measurement, and it should be same for all people for all times. So all the SI units, all the standards of measurement, they should be uniform, and all the countries have to come together, and that would, make the possibility of open trade, so people could exchange. So for example, I mean, you already work with the length and mass standards and so on. So if the nut and bolt manufactured in one country fits then the car or some machine manufactured in another country, so it makes the job easy, the trade easy. And these days, in the age of globalization, I think this becomes essential. So the SI unit has these 7 base units which are mentioned here, and since 2019, the SI system has been redefined, has been revised, and this is done, from time to time basis to improve the overall uncertainty and accuracies of all the units. So the system is redefined, and the latest modification, which was adopted in 2019, was to relate all the SI base units to their fundamental constants or fundamental properties of atoms and molecules. So this was done so that there is a uniformity, there is no dependence on the artifact. So the major change that had happened is the definition of 1 kilogram, which is now related to the Planck's constant, which was earlier based on the artifact, which we know. So India also had one prototype of mass, and this was the primary standard. But now people are going to realize the primary standard for mass, which is the Kibble balance, and the efforts are on even at NPL and many other NMIs. Many of the developed ones have already developed, and some are developing. So nevertheless, so in the redefined SI, another change that was done was it was made sure the interdependence of the base units. So time, as Mr. Ganesh also touched upon this concept, that time is the basic requirement. Time is the most accurately measured physical quantity, and for realizing 5 other SI units, you need to know the precise time. So that is the importance of time. So the time sits on top of all the other 7 base units, and this is the redefined order. So in addition to the redefinition, in terms of fundamental constant, the order of the SI units was also revised, and this has happened during the 26th Central Conference on Weights and Measures, and this was happened in November 2018 in Versailles, Paris. And our then director, Dr. Aswal, was there, who voted for the revised SI, along with the Secretary of Ministry of Consumer Affairs, Avinash Srivastava. You are well aware of that. So this was done at that point of time. So now coming to the topic of time. So because time is important, we know that time is forming the basis for even other SI units. So how we measure time and how we are doing it. So let's start with that. So any clock has two basic components. One thing is a frequency source, something which is periodically changing. Another thing is a counter. So to count those changes, and then of course there's a display. There can be an analog display or there can be a digital display. But the quality of a clock, so how stable and how accurate the clock will be, depends on the oscillator. So how the time measurement started. So the Earth is our natural oscillator. So because of its rotation, so the days and nights are happening, and still that forms the perception of time for us. Although we cannot guarantee accuracy, and when the sun is not there, I mean, there's no way to know what time it is. So fundamentally, the measurement of time started with the rotation of Earth, and then sundials were made. Egyptian obelisks were there, which were the first ones to realize or measure the unit of time. And then the pendulums came. So, and then the chronometers. So the sailors, the navigators, they didn't have the information. They could not derive it from the pendulum based clocks. So the chronometers came. So there were a lot of improvements that kept on happening in the journey of timekeeping to improve the accuracy of time measurement. And the latest invention is the wait a minute, I'll see if there is a pointer. I'll just take that. So the quartz oscillator, this is the latest invention, which is we all are using for our day-to-day applications. So this is a piezoelectric crystal. You apply electric field and it starts oscillations. And so this is an oscillator. So about 32.8 kilohertz is the natural frequency of oscillation at which it oscillates, and you measure it and then make a clock. But then it was decided that because quartz is good for our day-to-day applications, and some laboratory versions of quartz oscillators such as OCXO, temperature controlled quartz oscillator, or the oven controlled quartz oscillator are pretty good, which can manage time up to 10 to minus 9 kind of accuracy. But this was not enough, and on top of it, quartz is a man-made crystal. It is very much dependent on temperature and humidity variations, and it changes the frequency. So it's not an ideal option to make a universal standard, and that's how the age of atomic time began. So it was decided that atoms, why don't we take atoms as tiny oscillators? As you all know from the high school physics, that atoms have fixed energy levels, and there's E as E is equal to h nu, so there is a fixed frequency corresponding to designated levels of a designated atom, and it remains same all over the world. So it's fundamental, it's universal. So if you can measure this transition probability inside an atom, and you count them, you probe the atoms and count this transition probability, you can derive time. So that is the fundamental concept of the atomic clocks, and this field has been really phenomenal. And over the last 100 years, there have been 9 orders of magnitude improvement in the timekeeping accuracies, and with more than 10 Nobel Prizes have been given to the technologies developed in the area of time measurement, time and frequency measurement. So this is a fantastic field to work in. And here, if you see on this graph, so this shows you the journey of timekeeping from like about 1600 years century onwards. And you see there were initially pendulum clocks, mechanical clocks, there were various versions of clocks, and you see on the y-axis it shows the uncertainty of 1 second in about. So that is how the uncertainty kept on improving with the improved versions of clock. And in 1955, when the first cesium clock was developed at NPL UK, and after that there was no looking back. We were making leaps and bounds in the timekeeping accuracies. There were first cesium clock in 1955, and that is when in 1967 it was decided not to rely on Earth-based time, which was UT1 time scale. Because Earth's speed was changing and it is not constant, and we know that because of the mass distribution on the surface of Earth due to volcanic eruptions, due to tides, due to tectonic plate movements, the Earth is slowing down because of the mass distribution over its surface. So then it was decided that it is not a very good idea to rely on the solar time or the Earth rotation based time, and the definition was switched to the cesium atom. So in 1967, SI second was defined in terms of the frequency between the two hyperfine levels of cesium-133 atom, and this is the frequency 9192.631.770 Hertz, which is measured, and this is the characteristic cesium frequency which is measured in all the cesium clocks. So there were variations, and with the beginning of cesium clock, since this frequency 9192.631.770 Hertz lies in the microwave domain, so we also call them the microwave frequency standard. So the transition probability in an atom which we measure and which lies in the microwave domain are called the microwave frequency standards or microwave time standards. And there have been improvements even in the cesium clocks. So they were the first clock being developed at NPL UK, and then the laboratory versions were made at NIST and Paris and in PTB Germany. And the commercial cesium beam clocks were also made in US. And till date, there is a monopoly of one company, Microchip or Symmetricom. They have been taken over by others, which are making an excellent quality cesium beam clocks and which are being used worldwide as the workhorses for timekeeping. So there are about more than 300 cesium clocks, 350 cesium clocks to be precise, all over the world in different NMIs of the world, which are keeping the time on daily basis. So then the further improvement came with the cesium fountain clock, which I'll also touch later on in my presentation, and which was 2 orders of magnitude more accurate than the commercial cesium beam clocks or even the best laboratory versions of them. And then even the uncertainty of the cesium fountain clock was brought down, and the best cesium fountain clock has uncertainty of part in 10 to minus 16, which is phenomenal. But at the same time, after the invention of lasers and then the frequency comb, people could realize the optical clock. So in case of optical clocks, we are going to measure the transition probability, transition frequency, which is in the optical domain rather than the microwave, so in the terahertz domain. So if you are measuring a higher frequency, you are making more accurate clocks, which will also become clear when I touch this topic. So nevertheless, so we are making huge improvements in timekeeping accuracies, and we are still moving ahead. And optical clocks have been showing consistent better performance than microwave clocks, and you can can see, I mean, they would not lose or gain 1 second over the age of the universe, which is really amazing. We can measure fundamental constant, we can do some really high-end science, and even the practical applications are also there for optical clock, which I'll touch towards the end of my presentation. So this is how we are moving in terms of timekeeping. So now time is such an important quantity, and of course, being the NMI, NPL has been doing its job since its inception. NPL is keeping the Indian Standard Time for the country and disseminating it via various means. Initially, there were some satellite-based broadcast services which were available, and since 1974, when we procured the first atomic clock, of course, it was a commercial atomic cesium atomic clock which we procured. We have been maintaining the atomic time scale, generating Indian Standard Time since 1974. So we are realizing the IST and we are keeping it traceable to UTC at present within few nanosecond of accuracy. And we are also trying to make sure that we are able to disseminate IST to each and every user in the country. And if you look at the evolution of timekeeping in India, so you can have a look, like it was already there in this civilization. We already had water clocks. So our civilizations, as they say, is one of the most evolved civilizations. So you can see already the sign of that. And then there is on the Konark Sun Temple, there is also already a sundial. So you can have an idea of measurement of time from there. So and then in Jantar Mantar in Delhi and Jaipur, there are sundials where you can actually go and see the shades of sun falling, and there are some markings given, so you can have a fairly decent idea of what time of the day it is. And then in the 1974, of course, it was a news which came in the newspaper that NPL has procured the first atomic clock, and since then there's no looking back, and till date we are maintaining the atomic time scale for the country. So as we're talking about the atomic clock, so what exactly is an atomic clock? So how do we derive time from an atomic clock? So I'm sorry if the talk is too primitive for some of the listeners who probably already know about it. But just to give a decent idea to a general audience, I prefer to keep these slides to make a complete understanding on the time measurement. So in an atom, we already discussed, there are energy levels and there is a fixed frequency nu naught corresponding to the two designated energy levels in an atom. So of course, we can use atoms as tiny oscillators, which are a source of a constant frequency which they are producing, or which they are characterized for. So when we make an atomic clock, we have to choose suitable atoms. We have to choose suitable transitions. So it's not very easy, like you pick any kind of an atom and you can make an atomic clock. There are lots of details which go in, and then design of the clockwork, because you have to confine the atoms, you have to probe the atoms, so you have to have all the technology around it that you need. So suitable atoms, like for example, the alkali group 1 elements in the periodic table, so they have single unpaired electron, so they have very low ionization potential, so you can give a little energy to them, they can get excited, and then it becomes easier to play with these kind of atoms. So that is how all the alkali group 1 atoms, they are preferably used for making the atomic clock. So you look at hydrogen, you look at rubidium, you look at cesium. So cesium, of course, because of its, I'll come to that, why cesium is preferred for defining the SI second. Although we are using hydrogen masers, we are also using rubidium clocks, but cesium was preferred. And then choice of suitable transition. So at the time when the atomic clock development began in 1950s, so middle of the last century, so we didn't have the capability to measure optical frequencies very well. So the concept of optical clock was already well understood. Like if we go to higher frequencies, we make better clocks. But then we didn't have the means to measure optical frequencies very well before the dawn of frequency count, which helped us to measure, which gave us a scale to measure optical frequencies very well. But however, since the World War II time, we had the capability of measuring microwave frequencies very precisely. So at that time, another consideration was to look for an atom which has a transition which is in the microwave domain, where we can make a good estimate of their frequency. And of course, the design of the clockwork depends, and it varies from species to species. So if you make a cesium clock, it is not straightforward that you will make use the same technology and make a rubidium clock. There will be entirely different technology. And if you have to make a hydrogen maser, there is a entirely different technology. So confining a set of atoms, the technology changes how you confine them and how you probe them. So this is a basic block diagram of a atomic clock. So there is an atom, there is an atomic transition. that you know, and you decide that this is the atomic transition that we have to probe. So there is a synthesizer, and there is a local oscillator which is referencing to the synthesizer. So you excite the atoms with the frequency which is given from the synthesizer, and if the atoms are making the transition, you detect that transition. And if all the atoms are making the transition, so you know that your local oscillator is giving the right reference and your synthesizer is providing the correct frequency. And then you can have a feedback loop, a servo loop, to lock the frequency of the local oscillator to the atomic transition. And then if you can divide the frequency of this local oscillator, you can get 1 pulse per second, which is the important signal in time and frequency, which is basically the tick of the clock. So that is how you derive time from the atom. So there is a local oscillator, there is a synthesizer, you excite the atom, measure the transition probability, maximize the detection through a feedback loop, and at the maximum detection, you know that this is the correct frequency which atom is absorbing. So this is the atomic transition frequency, and then you lock the oscillator there with the help of the servo locking loop. And then you divide and get the 1 pulse per second to measure time. So then now we have to differentiate from like microwave second to an optical second. So we already know that there is a transition which has a certain width, and it is centered at some center frequency, which is like in the case of cesium is the 9192631,770 hertz. So now if we look at the clock instability, there is this relation for clock instability, which depends on the line width of this transition, also depends on the frequency of this transition, of course, the signal to noise ratio, the number of atoms that you are detecting, and the averaging time. So for the similar kind of line widths, if you increase the frequency, so your clock instability will reduce, because this is inversely proportional. So if your clock instability is reducing, that means you are making more stable clock, and at a fairly lower averaging time, you can get a better estimate of the actual frequency. And that is the difference between the microwave clocks and the optical clocks. So in microwave clocks, you are measuring a frequency which is 10 to 10 hertz, and in the optical range, when you go, you are measuring the frequency in the terahertz domain, which is 4 orders of magnitude higher. And if you have fairly the equal amount of the line width, the atomic line width that you are measuring, then you definitely have the advantage going from the microwave second to the optical second. So how does this actually differ? So in the case of microwave clock, so this is the basic block diagram which I just discussed in the earlier slide. So you have a local oscillator and you have a synthesizer. And in case of atomic microwave clocks like a cesium or rubidium, you have normally a quartz oscillator which works like a local oscillator, and you have a microwave synthesizer. So the quartz oscillator gives a 5 megahertz reference to the synthesizer, and synthesizer probes the atoms. While in case of the optical clocks, the local oscillator is changed by an ultra-stable laser locked onto a ULE cavity, and the synthesizer becomes a optical frequency comb. The rest of the clock work remains same, the principle remains same, only the local oscillator changes and the frequency comb changes. Of course, the atomic transition, because now you are measuring frequency in the optical domain instead of the microwave domain that you do. So that is the difference between the microwave clocks and the optical clocks. So then when we are talking about the microwave clocks, I just mentioned that the first atomic clock was developed at NPL UK in 1955. So this is the famous picture of Louis S.N. Perry, who developed the first atomic clock at NPL UK. And what goes inside, we have already, wait a minute, I think my PPT is stuck. I think there was an animation. I think I'll have to restart my presentation. I think there was an issue. I'll begin again and share. So are you able to see my slides again?
Yes, we are.
Okay. All right. Yeah, so we were on this slide. So what goes inside a cesium atomic clock? Of course, we have a model of the atomic clock at the NPL premises, and some of the legal metrology colleagues have already visited us. and it's very popular with the students and visitors alike, and you are most welcome to visit NPL to get a deeper insight. So what goes inside a cesium atomic clock, which was developed by SN and Berry, you have a cesium source and you have an inhomogeneous magnetic field to filter out, because at room temperature, there's a probability of atoms occupying the lower ground state and the excited state. So you want to send only one kind of state to the microwave cavity, otherwise there will be a mixing of states. So you deflect one kind of the state by inhomogeneous magnetic field, because this state has a different magnetic moment, and only one state of atoms are allowed to pass through the microwave cavity. And once they come out of the microwave cavity, if the frequency is correct, the atoms will make a change in their state. Another inhomogeneous magnetic field will deflect the states, and the changed state atoms will go and hit the detector. And if the micro frequency is not right, the atoms will not change their state and they'll go and hit the getter, which is kind of an adsorbent material, a bin for collecting the waste cesium atom, and the cycle begins. So this keeps on happening, and there is a feedback loop, a servo loop. So you keep on correcting the micro frequency until you detect the maximum detection. So once you have maximum detection, you lock the quartz oscillator to this atomic transition frequency, and this frequency output of the quartz is then as accurate and as stable as the atomic transition frequency. And from there you can do whatever. You can divide this frequency and get 1 pulse per second for measuring the time and the tick of the clock, or you can use the frequency reference directly. So this is what goes inside, and of course there are lots of details. The entire thing is done under ultra high vacuum, because you don't want other kind of atoms to collide with your cesium atom, changing their states. And there is an isolation which is provided by terms of magnetic shielding, because you don't want the atoms to interact with Earth's magnetic field or the stray magnetic fields present around, because you are measuring something with highest accuracy of the order of 10 to minus 13 or so. So this is from then in 1955 to today. We have now the commercial cesium beam clocks which are available, which are a tabletop device, and it's like 1 meter by 1 meter kind of a box which can be rack mounted. And these are the workhorses that we are using everywhere, and something similar the Department of Legal Metrology will also get in their project and at their RSL. So these workhorses will also sit there. And the accuracy of these clocks, which are fairly available in the market, is part in 10 to minus 13. So in the layman language, we'll say if this clock was to run continuously, this will not lose or gain 1 second in about like 30 to 40,000 years. So that is the kind of accuracy these kind of clocks have, and that is why they are fairly used for the timekeeping worldwide. So just a while ago, we were discussing like why cesium. So cesium atom is the alkali metal group 1, so low ionization potential, of course, low melting point, and at the room temperature, just to heat a little bit, and it's available in the vapor state. So you can probe these atoms well if they are in the vapor state. It's a single stable isotope, so you don't have you don't expect the mixing of isotopes which can change the energy levels. And these hyperfine levels, which are like this ground state hyperfine levels, which have the clock transition 9.192 gigahertz. They are fairly well separated and in the microwave frequency regime. And these are also very less sensitive to external perturbations. So you can make very accurate determination of this frequency. And that is how cesium was selected for defining the SI second. Okay, so what kind of microwave atomic clocks are available? And most of them are commercial clocks. So you have cesium thermal beam clocks which are available. You can even also buy rubidium clocks commercially. Lots of different versions and variants are available. And of course, ISRO, like they recently informed that they now have developed their own space qualified rubidium atomic clocks, which is a very welcome move and for the Atmanirbhar Bharat. So this is a very, very nice thing that has happened. And of course, hydrogen masers. So these are also the workhorses because they have excellent short-term stability. The cesium clocks have excellent long-term stability. So you marry the properties of both to make a stable time scale at all times, whether short-term or long-term. So these are the two workhorses which are being used continuously. And the other kind of microwave atomic clock, which is also called the primary standard, is the cesium fountain clock. So in case of cesium beam clock, you are having the hot atoms. So you are heating up the atoms and they are forming the atomic vapor and they're coming out. But in case of the cesium fountain, what you do, you want to slow down the atoms. So you employ the technique of laser cooling. So you shine laser beams from 6 orthogonal directions on the cesium atoms and slow them down. So this cooling doesn't mean the thermodynamic cooling, but you just slow down the atoms. You take the kinetic energy away from them in terms of the momentum transfer, and then you launch the atoms up through the microwave cavity. So the atoms move up and fall down through the microwave cavity, and then you detect the change of state. So the principle remains the same, which I had discussed in terms of the block diagram. Only thing the technology changes, you slow down the atoms. So since you have the slower atoms, so due to the Heisenberg uncertainty principles, you have increased the interaction time. So you make better estimate of frequency. So that is how these cesium fountain clocks, these are 2 orders of magnitude more accurate than the commercial cesium beam clocks which are available. And that is why they are called the primary standard of time and frequency. So I just discussed the laser cooling. So just to again explain, so if you have atoms are moving with thermal velocity at all times, even at room temperature, they are moving with speeds of like 200 to 300 meters per second. So if you have laser beam shining, which is at the frequency little less than the transition frequency of the atom. So this atom which is moving against the laser beam will see it upshifted due to the Doppler effect, and it will absorb the photon which is coming from this laser, and then it will emit the photon in a random direction, because it will go to the excited state and then release a photon in the random direction due to spontaneous emission, and then come back to the ground state, because that is its natural tendency. And this emission will be in a random direction, isotropic, and when a photon is released, there is a recoil. So the atom will get a kick in the opposite direction. So if you have similar kind of lasers, slightly red detuned to the atomic transition frequency, so the atom will start absorbing the photon in all the directions, and will in this process of there will be a net momentum transfer between the atom and the photon. And slowly, with billions and zillions of such cycles of emission and absorption, the atom will slow down. So we can reduce, often what we do in cesium fountain, from 200, 300 meter per second kind of speed at room temperature, we are cooling the atom down to 1 microkelvin. So 1 microkelvin will be equivalent to the velocity of 1 centimeter per second. So that is how. So when you have the atoms which are so slowly moving, so they'll stay together. So they'll behave like a macroscopic object. That is how we call them an atomic cloud. And we then push them together through the microwave cavity. They go like a macroscopic metal, like a ball you throw up, and it will come down after attaining the toss height, and then you measure the transition probability. So the rest of the stuff remains same, except that now you are employing laser cooling to cool the atoms down. So now the optical atomic clocks, we said, and now we are able to measure the optical frequencies very well, thanks to the invention of frequency comm. So there are 2 ways of doing optical atomic clocks, and here the atoms also change. So you can either do the neutral atoms trapped in optical lattice, and then you probe for their frequency, which is called optical lattice clocks. And these are being done by, with material like, these are transition metals like ytterbium, strontium, because they have forbidden transition in the optical domain, which can be probed. And here you have better signal to noise ratio, better stability. And other way to do it by trapping the single ions, and this is being done with various species like ytterbium ion, strontium ion, mercury ion, aluminium ion, calcium ion. All over the world, all the NMIs are working with different variations of optical clocks. So one way to do it, neutral atoms trapped in optical lattice. Another way to do is a single trapped ion. And of course at NPL also, we are making, we have started making one optical clock which is based on single trapped ytterbium ion. And these kind of clocks are at least 2 orders of magnitude better than their microwave counterparts. So now, because of such a phenomenal development of the optical clocks, there is a very nice discussion going on to define the SI second. So right now, the SI second is being defined on the cesium atom. And this was the time, 1967, when the SI second was defined in terms of the cesium atomic transition. And this is the time when the first cesium fountain appeared in 1994. And since then, the timekeeping accuracy has been improving. But at the same time, there was a concept of optical clock which was being probed, but of course, you were not getting very consistent measurement. But with the development of frequency comm, so this was a Nobel Prize invention. The frequency comm was developed at Germany in around 2000, and after that, there has been a rampant development of optical clocks based on different kind of species, and they are averaging down much faster. So they are giving much better accuracies, and they are even hitting 10 to minus 18. And in fact, now they are giving a very reproducible measurements, and interlab measurements are also going on between the optical clocks. So that is why the BIPM, the Consultative Committee on Time and Frequency, is actively involved to see if this SI second needs to be redefined in some near future because of their consistent performance. So what is the current status? I mean, this is being discussed, but and why it is being discussed? The cesium fountain clocks, now they have reached, as you can see, they are just tapering off. So there is no further improvement in accuracy which is foreseen. So they are already operating at the quantum projection noise limit. So no further development, no further improvement in accuracy is expected. So that is why people are now exploring the new domain, optical clocks. And now it is well understood, and they are consistently giving a better performance by at least an order wherever they are being developed. And even locally, they are comparing the optical clocks with fountains, and then they are making two versions, because fountain is an order of magnitude lower in performance than the optical clock. So now they are making two versions of optical clocks and then comparing the two with respect to each other. And in Europe, where there is a cluster of lots of nice NMIs, so they are all developing the optical clocks, and then they're comparing their optical clocks with each other. But the problem in comparing the optical clocks on intercontinental distances, for example, if you have to compare an optical clock developed in NICT Japan to optical clock developed in Europe, the time transfer technologies are still not present. So these kind of things are the challenges. Another thing is like, what is the technology that will go on? The strontium lattice clocks are behaving extremely well. They are giving reproducible measurements, but then ytterbium ion traps are also a fairly good candidate for defining the SI second. So what will happen? How will we define the SI second? Different species, different transitions, even in the same ytterbium atom, there are two transitions. So which transition, which clock transition will be selected, which candidate, no obvious advantage we can see at the moment. And then we need the time transfer techniques. And then there are, these clocks are so accurate, so there are some local gravity variations which are shifting the clock frequencies. So even that has to be taken care of. So what is the way forward? So CCTF, the Consultative Committee of Time and Frequency, which is the highest committee of time and frequency composed by the BIPM, so they have put up a way forward. So they said, okay, these clocks are very nicely producing the measurements of time. So we can accept them as a secondary representation of time. And they are nowadays being used. If you look at the circular T, they are now being used for steering the TAI already. And then they have prepared a detailed roadmap so that it is clear to the community when we can expect the redefinition of SI second. So this is the list of the secondary representation of second, the accepted definitions of secondary definitions of second which are accepted. So all these kind of clocks with these definitions and with these kind of uncertainties, they are now contributing to the TAI on regular basis. So the roadmap which has been laid out by the CCTF and at CIPM, so they say that at present, the microwave frequency standards are pretty sufficient for the kind of requirements, the time synchronization requirements, the application state, and even the time scale accuracies. They are fairly good enough for the time being. And let's go slow. Earlier, the SI redefinition was planned in 2026, but now that has been pushed back because people want to go slow because of the absence of time transfer, accurate time transfer methods. So optical fiber links are the time transfer methods, but on the intercontinental distances, there is still question. There is a all optical two-way time transfer system which is also being developed, but still it is at a nascent stage and it needs to be developed. And then people are working on the transportable optical clock. So if on an intercontinental basis, if you can't, lay down such optical links, but maybe you can have a transportable optical clock to calibrate the other clocks. So the complete understanding has to be developed, the reproducibility of the results, and then the CCTF has set a list of requirements for the SI definition. So at least this much improvement in accuracy, like an order of improvement of accuracy, and minimum of 5 optical standards producing that same kind of result. So there are set of criteria which has been put up by the CCTF and CIPM, and they're working on it. But just to give you a glimpse and an idea that the SI redefinition of SI second is in foresight, and this would happen in our lifetime, in less than a decade or so. So now coming to the UTC and the time scale. So because Mr. Ganesh also touched upon UTC, so Coordinated Universal Time, because it's a French acronym. So it's an international recognized atomic time scale, which is based on the SI definition of 1 second. So this the definition of UTC is coordinated by, it's given by the Indian International Telecommunication Union, and especially the group on radio astronomy. So they have defined as the time scale maintained by BIPM with assistance from IERS. IERS is the International Earth Rotation and Reference System, which forms the basis of coordinated dissemination of standard time and frequency signals. And it corresponds exactly in rate with TAI. TAI is the International Atomic Time, and it differs from UTC in the integral number of seconds. So UTC is corrected for the leap seconds, but the International Atomic Time is the time based on only the atomic clock data, which is not corrected for the leap seconds. And the leap seconds, whenever they are announced, that is the responsibility of IERS, and it's all well defined in nature. And why universal? Because it's same for all, and this in fact has replaced the GMT. Earlier we used to know the Greenwich Mean Time, which was when we were using the UT1, the definition of Earth rotation based definition of time scale. That has been now replaced by UTC, Coordinated Universal Time, although the UTC 0 also coincides with the GMT 0. So here, if you can see, there are time zones. The whole globe is divided in time zones, and this is just because our biological clocks work with the solar cycle, so we have to make sure that we save the daylight time, and we work at our best efficiency, which is during the time when the sun is present. So the whole world is divided with these, lines, which are called longitudes, and at every 15 degrees, you have 1 hour time difference. So the whole world is divided into time zones, and the UTC 0, however, was made sure to coincide with the GMT 0. And India is sitting 5.5 hours ahead of the UTC. And as you go on the other side, they are lagging behind the UTC in number of hours. So that is how you can, if you know UTC, you just have to add the time zone difference, and then you know the local time at your present location. So how time is managed globally? So this is a question which everybody thinks. So now there are atomic clocks in all the NMIs. So NIST is the NMI of US, PTB Germany is the NMI for Germany, NICT is for Japan, NIM for China, and NPLI for India. So all these clocks are having atomic clocks, and they all have the time transfer links. So the clock data and the time transfer data on daily basis is sent to BIPM servers. So there's a misconception. Sometimes we think that the time is transmitted through satellite. So it's not the time which is transmitted through satellite, it's the time transfer data. So we just use the satellite signal to compare our local clock with the satellite clock, and we save that data in our server, and that this data is what we upload to the BIPM, not a signal that we are sending through the satellite. So BIPM, when it collects the data, so it makes a weighted average. So about 500 atomic clocks, which includes the cesium clocks primarily, more than 350, and then hydrogen masers. So recently, with the revised algorithm, the hydrogen masers are getting good amount of weight. So these clocks, in about 80 laboratories, the data is being sent to BIPM, and BIPM generates a free atomic timescale. EAL is basically a French acronym which stands for the free atomic timescale. So this is the weighted average of clocks. So each clock at the BIPM is given a weight and a rate based on its performance, and the whole data is taken to derive a timescale, which is a statistical timescale, a paper timescale, which is called free atomic timescale. Now, this free atomic timescale is tiered for the SI definition of second, which is obtained from the primary standards like cesium fountains, or some secondary representation of second, which are also accepted for steering of time. So that data is given, that is fed to an algorithm. So this looks very simple, but this is all very complicated because there are rigorous algorithms, filtering algorithms, and so many details, the PLLs and all. So it's quite a complicated scheme which is taken care by BIPM. So they take the data and steer this free atomic timescale, and the timescale that you get in return is the international atomic time, which is corrected for the SI definition of 1 second. Now this TAI, you have this International Earth Rotation Reference System, which is measuring the rotation of Earth, and which has the UT1, which is the timescale which was the earlier timescale we were using, which is based on the rotation of Earth. And what it does is, based on the Earth speed, it is maintaining UT1. And whenever the time difference between UTC and UT1 goes beyond 0.9 second, the IERS announces insertion of a leap second. So far what we have seen is Earth is slowing down. So then we are always adding the leap second. So because the atomic time scale, which is the UTC, has to work along with the UT1, because otherwise our biological clocks will not work very well. So this was an agreement which was reached. So this is, although till date only 37 leap seconds have been added, but there is a complete mechanism in place in case of a severe change in the speed of rotation of Earth. If it becomes fast or too slow, at least we have in place a system where we can be, correcting the atomic time to keep it go along with the biological clocks of ours, which is based on the solar time. So, but of course, there are a lot of discussion, because most of the electronic systems and computer systems, they don't like this thing, because one time step is added, 1 second is added. So there is a lot of discussion going on, but at least for the time being, this is how it is done. And this UTC is published on a monthly basis by BIPM in the form of a magazine which is called UTC Circular T, which tells you the UTC minus UTCK. UTCK stands for the lab. So then this difference is available. Now a local lab like NPLI, which already has its time scale, we also do a local ensembling, a steering algorithm we have in place based on the performance of all clocks. But only one clock can be a flywheel oscillator. For in our case, we are using an active hydrogen maser, and we have a steering device. So we have an algorithm which predicts the correction to be applied to the steering device. Now we can choose if we want to apply steering once a daily in 5 years, 5 days duration, or in once a month. That depends on how well we want to keep our time scale stable, and how well we want to our time scale to follow the UTC. So the idea is to do both, to have it stable, but as well as it has to follow UTC, so that the difference between UTC and UTCK is minimized. So this data from Circular T is taken also for steering. So one steering we do based on the local ensemble, and the other steering we do on the basis of UTC minus UTCK. So what we realize is a local realization of UTC that we do at NPL, and we add 5.5 hours to it, and that is what we get as Indian Standard Time. So it's not easy, I said. There is a well thought steering algorithm which BIPM takes care of. So again, the free atomic time scale, which is based on the weighted average. Now, if we see at a lab level, the local realization of UTC is done on a lab level. It has a bank of clocks, which can be a combination of hydrogen masers and cesium clock. Then it has its own steering algorithm. Then it has a microphase stepper, which is basically the steering device. And then what you get is a UTC lab. And the flywheel oscillator can be, normally it's a hydrogen maser because of its excellent short-term stability. And that is how we realize the time scale at the lab level. So now at BIPM level, what they do, they are having a unique code assigned to each of the clock. So for instance, if a lab has 5 clocks, so BIPM, how it will put up the algorithm, it will assign a weight to each of the clock. It also gives weightage to the predictability of the clock. For example, the hydrogen masers, they are extremely predictable. They have a constant drift which can be removed and taken care of. So that prediction, because of their good predictability, they are given more weightage at the BIPM. And then the clock differences on daily basis they are measuring. So all this is taken care, and an algorithm is placed for generating the free atomic time scale at BIPM. And then what you do for TAI, you add a correction F, which is based on the primary standards, because the free atomic time scale needs to be steered to maintain agreement with the SI definition of 1 second, and that is how you get TAI. And in the TAI, then you add the leap seconds and you get UTC. So this all is done with rigorous time scales at BIPM. So the time we just discussed that at lab level, we have the atomic clocks, of course, and lots of precision measurement equipment, and we also have time links. So this is a data of the whole globe, and the NMIs having the two-way and GNSS equipment, that they are shown with the green dots, and those having only the GNSS equipment. So these are the two techniques for the satellite time transfer or the comparison. The time comparison data that BIPM needs is either with the GNSS or with both two-way and GNSS. At least one of them is necessary to keep the traceability. So this becomes challenging, and we have to ensure that these satellite links are operational at all times, and so that we don't lose our traceability at any point of time. And for this purpose, we have multiple layer of power backups. We ensure that the antennas have clear visibility, and everything else has to be maintained in good shape. And of course, the environmental conditions. And I think the legal metrology people are now very well aware, because we are setting up the time labs at various RSLs, and we are taking care of all these things. And initially there were apprehensions like why so much detail is required, but soon you will realize that all this was really a requirement to keep stable time scales. Okay, so then coming to the time dissemination. So far the time scale, how time is managed globally and at the lab level. So once we have a stable time with us, so the next mandate, like for an NMI, is to disseminate. And time dissemination, if you want to do it with extreme accuracy, with nanosecond level accuracy, then there are satellite techniques, which are common view global navigation satellite systems, like CV-GPS is the most common one we are using. GLONASS is already there. And then CV-NAVIC that we are talking about, and Mr. Ganesh also mentioned this. And another is a two-way satellite time and frequency transfer system, which can give you an accuracy of less than 1 nanosecond. And in fact, the NAVIC ground stations at Lucknow and Bangalore from NPL, they are getting traceability by both the means. So they have both the connection as redundant connection, so that they don't lose the traceability to IST. So both the links are set up, and because of the requirement, they definitely need nanosecond level of accuracy. Another way is public switch telephone network. So dial-up techniques. Earlier we had teleclock, now we have phonoclocks, speaking clocks, and many of the countries are still going with it. It's a very popular means and very secure means of disseminating time, although the accuracy is limited to millisecond domain. Another most popular in today's time is the network time dissemination, and this is done by NTP, PTP, and recently even White Rabbit. So NTP is commonplace within millisecond accuracy, and of course this is the first thing that you would implement even at RRSLs, because of its ease of implementation and millisecond level kind of dissemination. You can easily begin, and commercial servers are available which can handle a large capacity, large number of hits, and most of the people I think can do with millisecond level of accuracy, like even digital time stamping and even the IT companies and so on. And even for cyber trails, I think to some extent, even the NTP is good enough to start with. PTP is a precision time protocol, which can give you microsecond level of accuracy, but not in the wide area network, but in local area network or through direct optical fiber. And in fact, White Rabbit is an advanced version of the same. And these kind of systems are required for stock markets, for banking, for high frequency transactions, even for smart grids and so on. And even the telecom sector is relying too much on PTP and White Rabbit based systems. And worldwide also, there is a lot of emphasis on these systems, but these are, again, these are commercially available, but a bit complicated to establish and implement, but this is the need of our, we have to get into it. Another popular means which has been put in place in many countries around the world is the long wave radio transmission. So radio clocks. This is a fairly, this is a very old technique, but very reliable one. In fact, if you lose your satellite links and you don't have anything else, if you have long wave radio, which is fairly in your control, one can disseminate time with millisecond accuracy easily. And India has been trying to, there has been efforts to establish a long wave radio system, but still it's not there. It will be great to have such a system in place. Direct calibration, of course, what we provide through Center for Calibration and Testing, and optical fiber links is the way forward, because the optical clocks are being compared with noise compensated optical fiber, coherent fiber links, but these are fairly complicated, and long distance transmission is still very much limited, although Europe has demonstrated even up to 1,000 meters successful comparison of even optical clocks, which are accurate to apart in 10 to 18. So they are doing it fantastically, but still long distance and intercontinental time transfer is still a question. So long wave radio, as I said, because other techniques are fairly known. I think everybody knows about, the telephone clocks and network time systems, satellite, I'll also talk a little bit about, but the long wave radio. So these are fairly tall towers operating at like about 100 kilohertz kind of a low frequency. So it will have a ground wave component and a space wave component. Space wave component gets attenuated and reflected multiple times through ionosphere, so we can ignore that. But the ground wave can penetrate a long distance, and in fact, they can have a good field strength even up to 1,000 kilometers. So if you install one tower, so it will take care of that diameter of 2,000 kilometers around its location. So this can be a fantastic means of time dissemination, although it's an old technique, but still fairly relevant. So one can have a ground station with atomic clocks at the base of the tower, and the tower can be sending the time signals, which can be encrypted ones, and there can be a small receivers, chip scale receivers in the various systems like mobile phones and clocks. And in fact, in Europe and in Japan and even in China, they have such systems. You don't have to adjust your clock. Your clock will adjust automatically wherever you move based on the signals received. So this is quite a good means of doing it. And in Japan, so this is the picture of the tower that they have at Otakodaya. And this is about like I think 150 meters tall tower, which is disseminating time signals. And they are not just used for clocks or for time applications, but for even disaster management, for even traffic management, for power grids and all. They are using this. So similar things even in India can be done in future. So CV Genesis, I think I don't need to say much because Mr. Ganesh has already told about it. So if you have two clocks remotely located, but if you have a common satellite in view, so then with a simple equation, you can locally you will be having clock A minus the satellite clock, or if you have GPS, so the GPS clock, and you will locally have satellite clock minus B. So since satellite clock is common, so eventually you will get clock A minus B. But of course, you'll have to take care of the delays which are there, the path differences. Which the signals take to travel from one station to another station. So this can be done. So as I already mentioned, so we are giving traceability to ISRO via CV GPS mode. For enabling their NAVIC, which is Desi GPS system. And there are lots of GNSS systems in place. GPS is owned by US, GLONASS by Russia, Galileo by EU. It's fairly rapidly coming up. Beidou by China, and of course INSS or NAVIC for India. So once we have NAVIC receivers, timing receivers already there, so we can be doing CB NAVIC. So we can be getting rid of CB GPS. But for the time being, we have kept both because we have to keep redundancy. So there is a two-way time transfer system, which is fairly, the best means, I would say, for having the nanosecond accuracy to compare time between two remotely located clocks. And here the case is because you are using satellite as a reflector, so you're doing a full duplex communication. So you are sending and receiving signal at both the stations. So that helps you get rid of lots of delays because they cancel out, because it's a symmetric system. And also the Sagnac effect has to be taken care of. But these are fairly well evaluated, well calibrated, and you can set up the system, evaluate all the delays, and make sure that you can get less than 1 nanosecond accuracy. And Mr. Ganesh has already informed that they are keeping their NAVIC time traceable to IST with two-way time system, which is working fantastically well and within 1 nanosecond accuracy. And in fact, at NPL, we also have an international two-way system for the traceability to UTC. So if I put up a comparison of various time transfer technologies, so the long wave radio, GPS, even GSM network, internet, fixed line. So all of them are, as an NMI has to have all the means of time dissemination, but long wave, of course, has a certain advantage only if we talk about in the millisecond domain, because these can penetrate well even in the indoors or underwater, and you don't need big time antennas, so it's fairly good. But I think internet is equally good means for millisecond accuracy. But for the critical applications like space and even the stock markets and so on, I think one has to rely on better modes of time dissemination. So what does NPL do exactly? So in this whole jargon of time and frequency metrology, so like contributing to TAI is of course one thing that NPL does on a regular basis, and maintains the traceability of IST to UTC within few nanosecond accuracy. And with circular T published every month, we steer the UTC NPLI. And in future, because we have the primary standard of time and frequency, we have developed the cesium fountain. If we keep it running all the time, we can be steering the UTC NPLI with the fountain data, and which would make us really independent. We don't even need, because the circular T data has a latency of 1 month because it's published only once a month. So if you want, but if you can steer with the primary standard, which is realizing the SI definition of 1 second, so you can have a much accurate time scale and you are not dependent on even the satellite links or other signals in case you lose them. So the laboratories at PTB Germany, in French laboratory, even USNO, they have already demonstrated their timescale steering with the fountain data. And they have improved their performance considerably and significantly with the addition of fountain in the timescale steering algorithm. And this is something similar even at NPL we would like to do. So at NPL, we do all modes of time and frequency metrology. We are having our primary standard. We are even developing an octet clock. We are having a very extremely stable time scale, which is following the UTC within plus minus 2 nanoseconds since last couple of years. And then, of course, we have time dissemination means. At present, internet, telephone, and satellites are the means we use for disseminating the IST to common users. So on the R&D level, what NPL does, we have the first cesium fountain clock, which is approved as a primary frequency standard. We are making a second version of it. The accuracy of such standards is 10 to minus 15 to minus 16 order. So if these were to operate continuously, they will not lose or gain 1 second in more than lakh years. And then we are also developing Gitavian ion octet clock, which will be a future standard, which will be accurate to even 2 orders of magnitude better. So this fountain clock we developed indigenously. So these kind of clocks are present in only less than 10 laboratories, 10 countries around the world, and India is proud to be one of them. And under the mentorship of Dr. Amitabh Sen Gupta, we developed this and we got it approved. And you can see at at less than 1 day, it already approaches the stability of 10 to minus 15. So if we can run this fountain continuously, we can steer our time scale. That is what probably Mr. Ganesh also meant by having a strong NPL. And we are now putting the thrust on this area by coming back to our R&D and significantly improve so that we can even run the first fountain, develop the second one, and even continue our work on the octet clock, and which is going to be the future standard. So our data was already, the fountain data was already published in Circular T and was used for the steering of TAI. And this was the big step forward. I mean, for India to come in the league of top 10 countries doing it, and we are very proud of this. And we want to continue with this. So at the CCTF, the Consultative Committee of Time and Frequency, which meeting took place in 2015, it approved the NPL India fountain as the primary frequency standard. And at one point of time, I think around 10 to 12 fountain reports are published in every Circular T for steering of TAI. And India wants to continue with this again. So, and what we do is a generation on dissemination of IST. So we have a primary time scale, we have a backup time scale, and we have the time scale links. And with this, we are keeping IST traceable to UTC, and then we are disseminating at present with satellite means and the internet means, and the telephone time system is also there. But at the moment, it is being used only in-house. And how we keep it traceable to UTC, and we were very happy to reduce the uncertainty. And at the in 2018, we could have the uncertainty as low as, which was the lowest possible uncertainty for Indian Standard Time, with the 2.8 nanosecond. So we have the time scale system, we have the satellite links, and with this satellite links, we are traceable to UTC with plus minus 2.8 nanosecond accuracy, and we are among the leading timekeepers. So doing pretty well. So this was the data taken from Circular T and published in 2018. So I think that for the time scale, I think we are doing pretty well globally. And this is the performance of UTC NPLI from 2016 to 2022. And you can see initially there were large variations, but from 2020 onwards, suddenly we are improving the time scale, and now we are able to keep the time scale within plus minus 5 nanosecond. And this happened because we are having the better timescale algorithm, and also the better hydrogen maser, active hydrogen maser, which are extremely stable and predictable. And that is how our timescale performance has improved. We could keep it for more than a year. We could keep the timescale difference between UTC and UTC NPLI to plus minus 2 nanosecond, but of late it is again drifting. So if we have a fountain data steering, if we can use the fountain, we can keep this difference between UTC and UTC NPLI to within plus minus 2 nanosecond, which other laboratories are already doing. So for the IST dissemination, what NPL does, we have our NTP service. So we have more than 1 lakh users, and these users are going to increase based on the recent CERT guidelines. So we expect a lot of people to hit on our NTP service. And this is right now a freely available NTP service is at this domain name. And we also have a web time display, which is available on the NPL website. And you can also get to know how you can synchronize your device time to the IST, which is available through the NTP service of NPL. Another way is via CBGNSS and two-way time and frequency transfer system. And this is how we are providing the traceability to ISRO. So IST, and then we have the two-way satellite link, which ISRO mentioned, like Mr. Ganesh mentioned, that they have set up the two-way satellite link along with the CBGNSS link. And we are located here, and we are giving the traceability by CBGNSS and two-way satellite transfer means to their Navik time centers at Lucknow and Bangalore. And these are the ground stations for Navik satellites. So all the Navik satellites are traceable to IST within nanosecond accuracy. So this is how we are disseminating time to critical users such as ISRO. So for with the mission of NPL towards nationwide time synchronization, so we want to have all the means available for time dissemination so that each and every user can access the Indian Standard Time. And for that, of course, we have this NTP service, which is right now freely available, and we want to strengthen it further so that we can give a fail-proof service to all. And we are even thinking of an interface so that we can have a 24/7 fail-proof NTP service, which is the need of the hour based on the CERT guidelines. We already have a telephone time dissemination service, but in the absence of legalization, I think it's not going to see the light of the day. Long wave radio, we already signed the MOU with the Mrs. IFR for setting up the long wave radio towers, but I think it's taking time, but it will be really useful and good, I mean, to have this option of time dissemination in country as such. And then we have already signed an MOU with DOT. They also want to synchronize because for the 5G communication, at least it's mandatory that their base stations are synchronized to within few nanosecond accuracy. So they have to develop their secondary time centers. Otherwise, it will be difficult, or they have to devise some means to take the traceability from the RSL centers being developed under the project that we are already executing with the Ministry of Consumer Affairs. And CVGNS and two-way time transfer systems, anyway, these traceability means are already available with NPL. So towards legalization of IST, so we are already having this legal metrology project. So in today's presentation, probably is beyond the scope of today's presentation, but we know that we are developing 5 timing labs at 5 RSL locations, and these will all be traceable to IST via CV GNSS means initially, and then probably we can switch over to completely CV Navik. And these 5 centers will then become the regional IST dissemination centers, and to make IST available to large set of users. And probably after we make the IST available, we can push for the legalization. So right now, IST is not the legal time of the country, while in many countries, like in Germany, in US, and so on, their time kept by the NMI is the legal time of the country. So something similar in India, we also have to have, and probably that is why the purpose of this project. And once this project is successfully implemented, I think we will also be able to define the legal time for the country. So now coming to the applications and why are we going towards atomic clocks and still improving the timekeeping accuracies? So who needs it? Why is it important? So we are talking, of accuracy in terms of part in 10 to minus 15. So which is like the present accuracy of our cesium fountain. So having such an accuracy would mean that we are able to measure the distance between Earth and Sun with 0.1 millimeter accuracy. And and for the optical clocks, where we are expecting them to be accurate to part in 10 to 18, these will be not losing or gaining 1 second over the entire age of universe. So who needs such high precision and such fantastic timekeeping accuracies? Of course, present day financial transactions, smart power grid, AI, IoT, they are all dependent on time synchronization up to a level of microsecond to nanosecond. But with optical clocks, we can have better time scales, more stable, more accurate time scales, and where you will be reaching the stability, the required stability in shorter averaging times. And for better navigation, for communication, for deep space exploration, for VLBI and so on, we need such accuracies, and even for geodesy, for Earth's gravitational potential determination. So geoid is an imaginary surface, but it's not so accurate. So with the optical clocks, we can be measuring the gravitational potential at local places extremely well, and we can have a better defined gravitational potential or geoid around the Earth. So the applications, already was touched by Mr. Ganesh with the NAVIC, with the Global Navigation Satellite System. So all the satellites, they have atomic clocks on board, and the satellites are at their positions, and then they transmit their position and the time taken by the signal to reach. So we'll be able, so this is symmetrically radiated in all directions. So we'll be having a circle with a known distance, but this will not be able to define the position very well. So this is the method of trilateration. So you have another satellite and the signal coming from the other satellite. So you have the arcs, the signals, they're intersecting at 2 points if these are the circles. So still you don't know the position very well, but if you have this third satellite in view and all the atomic clocks are synchronized, so you'll be able to define the position well. So in the 3 dimension, if you have a fourth satellite, so you define X, Y, Z and also time. So that is how we are able to get navigation accuracies, because all the onboard satellite clocks, they are on all the satellites, they have atomic clocks which are synchronized with each other. So ticks of all the clocks are synchronized with each other with nanosecond accuracy, and that is how, if they are accurate to within 10 nanosecond, we get a position accuracy of 3 meter. So if you have microsecond level of difference is there between the satellite clocks, we'll be reaching probably a kilometer away from our destination. So in cyber security, another very important application where time is required. So to have a chronological trail of events for cyber forensics, so at the average time of hours each user is spending on internet is increasing by each day. So there was some report like on an average, 18 hours per month an average person spends on internet. And if you don't have a trail of time, if you don't have the trail of events which are synchronized to one common user, it will be very difficult for the cyber forensics to track a certain event. And that is how the cyber criminals are taking the advantage if the time is not synchronized. So lots of bank frauds and threats, and even on the voice over internet protocol, so many wrong means are being adopted for with wrong intentions. And it is very important for country cyber security if the time is synchronized to one common reference source. And in financial sector, nowadays we are having high financial trading in stock markets, and if the time is not synchronized to a microsecond level domain, so you will be gaining or losing a lot of money, and which is not good. So recently there were report of Bangladesh bank being hacked, the New York Stock Exchange flash crash, and a very recent scam of National Stock Exchange in India of the co-located servers, where they got an advantage by placing their servers very close to the stock exchange servers, and in the high frequency trading some people made a lot of money by wrong means. So it's extremely important for the financial sector to be time synchronized to one common source. And with the report, the cybercrime in India is increasing each day. So one cybercrime in India every 10 minutes is happening, and the CERT India team, which is now making mandatory for everyone to synchronize their devices to NPL time, the cybercrime, the 50,000 cases are being registered by CERT in team, and that's why they are forced to now issue a mandate that everyone should synchronize to NPL time. So, and then in the coming times, as the digital economy is growing, so we have to take care of this aspect in our financial domain. So synchronization to IST is indeed a requirement, and that is how the importance of time secondary time centers that we are establishing under the legal metrology project. And of course, there are lots of applications, relevance of time synchronization in various sectors such as transport, smart grids, banking, cybersecurity, telecommunication. For the NAVIC already we are serving, and all the national emissions. So if all the clocks are synchronized to IST, we can boost our economy, and we can also make the Digital India program cyber secure. So in summary, to summarize, so I've given a large, range of information to you, but just to summarize or get a take-home message. So there has been remarkable progress in timekeeping, and it is still going on. And especially in last half a decade, just over a half a decade, there have been lots of improvements with the advent of atomic clocks. So the present SI definition is based on cesium atom, but maybe soon it can be based on an optical transition. So some redefinition of SI second is on the cards. NPL is the NMI and the timekeeper of the nation, maintaining IST, keeping it traceable to UTC, and disseminating to all the users. And most of the modern applications like finance, cybersecurity, telecommunication, navigation, all of them depend on precise time, and time synchronization to one common source is essential to avoid any chaos for all critical applications. And there is still a lot to come. We have moved from the microwave second to the optical second. That I described during my talk, and in future we are even looking at the nuclear clocks, where we'll be measuring the frequencies of the nuclear vibrations. So there's still a lot to go in the timekeeping domain, and one has to stay abreast with all the developments happening in this field. And of course, NPL is doing its part along with ISRO. I think time and frequency metrology in India is on the right track, but we have to definitely make a lot of progress with lots of indigenous developments like Fountain we have developed. ISRO is making rubidium atomic clocks. So in future, if we keep on the right track, we can be leading India towards Atmanirbharta, at least in time and frequency domain. So with this, I would like to thank you all for your attention. It was a long talk, but I think it was necessary to give the complete overview to all the stakeholders present. So if there are any questions, I'll be very happy to take them. Thank you very much.
Thank you. Thank you very much, madam. You have explained it in a very well manner. It's just a precise from the beginning to the end, and what is in the progress, what is in the future. Thank you very much for your these best presentation. And I would like to request you if you can share few slides. I will send it to the participants. They will understand what is actually which are not confidential or which can be shared with the participants. You kindly give me few of the slides, and so that it can be shared with the participants. I would like to thank my additional secretary, ma'am, my director, sir, and all the participants with NIC team who is actually working for making these programs on Saturdays. Otherwise, it is not possible. If they are not there, we cannot do anything. This is all game behind this is of NIC. And I would like to thank all the participants, all the panelists, including Dr. Poonam Arora, Mr. Ganeshan, who are the experts in the field and day and night working for the development of the country. With these remarks, I would like to thank everybody. Thank you very much. And if there will be any questions, certainly we will share to you. Thanks to all. Thank you very much, sir. Let us have thank you very much.
Thank you, Ashutosh ji,
Thank you very much,
for
sir. Thank you.
organizing such nice program every Saturday.
Thank you, sir. Thank you. My pleasure.
Thank you.